My name is Fengnan Huang. I'm from National Central University. I'm one of the organizers of this short course. And it's our pleasure to invite Professor Kengo Nakajima. He is an expert in supercomputing and iterative method for solving partial differential equation. So it's a great honor to have him to give us a 5-day short course. So he was begin by very beginning finite element methods. Then we also have hands-on sections. Because the size of this class is not big, so I think we have more chance to interact with Professor Kengo Nakajima. And also he provide a count using the supercomputer in Tokyo. So that is great opportunity to use the state-of-the-art supercomputer system in the world. So I hope you enjoy the course and learn basic finite element methods and pair computing. So let's welcome Professor Nakajima.
Professor Wang, for a kind introduction. So my name is Kengo Nakajima. So I'm very happy to back here. So actually, I gave a lecture here in this February. It's 3 days, a little bit different topic. And I found some familiar faces here. So I'm happy to meet all of you. Okay, so as Fennan mentioned, so this time I'm giving class lectures and hands-on related to the finite element method and the parallel finite element method. Okay, so let's start the introduction. So you can find some material on this website, as you have already known. Okay, so this is the I start from the target, and I just overview the very general issues about the supercomputers and the computational science, and the overview of this class and some future issues. Okay, so I just read this. So this 5-day intensive course provides introduction to large-scale scientific computing using the most advanced massively parallel supercomputers. So topics covers finite element method, message passing interface, MPI, parallel finite element using MPI and OpenMP, and parallel numerical algorithms for iterative linear solvers. So several samples programs will be provided, and participants can review the content of lectures through hands-on exercises using Wisteria VDX Odyssey with A64FX processors at the University of Tokyo. So finite element method is widely used for solving various types of real-world scientific and engineering problems, such as structural analysis, fluid dynamics, electromagnetics, and etc. So this lecture course provides brief introduction to produce procedures of finite elements for 1D, 3D steady-state heat transfer, heat conduction problems with the iterative linear solvers and to parallel finite element method. So lectures for parallel finite element will be focused on design of data structure of distributed local mesh files, which is the key issue to the efficient parallel finite element method. So I highlighted this part in the bold red letters. So actually, this class provides information about the grammar of the parallel computing, such as the MPI or OpenMP. But so this kind of the design of the application for parallel computing is the most important part. And I hope you can learn both of the very fundamental programming techniques using MPI and also how to design the parallel applications. Okay? So that's the purpose of this class. So introduction to MPI, so message passing interface, which is widely used method as de facto standard for the parallel programming is also provided. And solving large-scale linear equations with first quotient matrix is the most expensive and important part of the finite element, and other methods for scientific computing, such as finite difference, finite volume, etc. And recently, families of Kirillov iterative solvers are widely used for this process. So in this course, details of implementations of parallel Kirillov iterative method are provided along with parallel finite element method. So as Professor Huang introduced, so my current background is this part. But so this time I just show you the very simple method. But so you can learn something from this. And finally, lectures on programming for multi-core architectures will be also given along with a brief introduction to OpenMP and OpenMP MPI hybrid parallel programming model. So this February, I just focus on the OpenMP parallel programming model. And this time, we learn MPI, and we combine these for the massively parallel supercomputing. Okay. So motivations for parallel computing of this class is large-scale parallel computers enables fast computing in large-scale scientific simulations with detailed models, and computational science develops new frontiers of the science and engineering. So this picture is Professor Manabe. He's originally from Japan, and he's working in USA now. And he received a Nobel Prize in Physics in 2021. So he's a specialist and pioneer of the climate modeling, so using supercomputers. And basically, this winners of the Nobel Prize in Physics are particle physics or energy physics or something like that, very fundamental physics. And he's a earth science person. So it's a very rare case. And moreover, he's a specialist with supercomputing. And so I'm a member of the community of the high performance computing. Yeah, it's a very great honor, and also it's a epoch-making event. So anyway, so this is a very important issue. Okay, so why do we do the parallel computing? So one purpose is the faster and larger. So larger is more important from the viewpoint of the new frontiers of the science and engineering, but faster is also important. And we also do the more complicated computing by the large-scale parallel computing. From the viewpoint of the computing or computing performance, so ideal status is a scalable. So we have two types of the scalable. One is weak scaling and strong scaling. So solving n times scale problems using n times computational resources during the same computation time. So this is mainly focusing on the large scale problems. So this type of the scaling is called weak scaling or weak scalability. And in this class, you learn about the conjugate gradient solver, but generally we need more iterations for the larger problems. So actually it's not so easy. Okay. So next one is solving problems using n times computational resources during 1/n computation time. Probably this is more familiar with you. So it's mainly focusing on the faster computation. So this is called strong scaling and strong scalability. So in this class, we are mainly focusing on the strong scalability. Okay, so let me introduce myself briefly. So I'm now working for the faculty member of the Supercomputing Research Divisions of the Information Technology Center of the University of Tokyo. And also I'm a faculty member of some other department of the Mathematical Informatics and the Department of WE in University of Tokyo. And since 2018 April, 5 years ago, I'm also a deputy director of the Riken Center for Computational Science. So it's a home of the Fugaku supercomputer. So actually, 80% of my salary is from University of Tokyo and 20% from Riken. So in Japan, we have this type of hiring style is now emerging. So my main research interest is high performance computing, parallel numerical linear algebra, especially on the preconditioning, parallel programming model, computational mechanics, computational fluid dynamics, and adaptive mesh refinement, and parallel visualization. So I received my bachelor's degree from the University of Tokyo many years ago. So actually I'm now 60 years old. okay, and 61 in this September. And so my master's degree is from University of Texas, and so doctoral degree is again from the University of Tokyo. And actually, so after finishing my undergraduate, I worked for industry for a long time, Mitsubishi Research Institute. And so I moved to the research organization. And 20 years ago, so I joined the University of Tokyo. And so actually, I started my career in the university in the Department of the Earth and Planetary Science. So, and after that, I switched to the Information Technology Center. It's a supercomputer center of the University of Tokyo. Okay, so in this class, we are learning about the scientific computing. So scientific computing is a very sophisticated and a very complicated structures. So I call this SMASH. Okay? SMASH means science, modeling, algorithms, and software and hardware. So this means so you can so you have to learn many things. And so in other point of view, collaborations or co-design will be important for future career of each of you and other scientists and or engineers. So you have to communicate with people with different backgrounds, and it is more difficult than communicating with foreign scientists from same area. So actually, so Professor Huang and I are friends in recent 20 years, and we are from the same background. So usually we communicate in English. It's not a mother tongue, but we can communicate very smoothly. And so around me, so there are many system scientists, and they are very from the different background. So sometimes, even in Japanese, it's very difficult to communicate with them. So I think so you have already had same experiences, but you need to communicate with them to do this type of things. And so I understand you are from the many kinds of the background, but so this time you try to extend your expertise to communicate with other areas, people in the future. Okay, so how many of you are from the mathematics department? Okay, thank you. So how about natural science, physics, chemistry? Okay, thank you. And how about engineering? No engineering. How about computer science? Okay, so mainly from the mathematics and natural science. So fundamental study. Okay, okay, that's fine. Okay, so in this class, so science is a parallel finite element using MPI and OpenMP. And so science is heat conductions. So this is the target. And the modeling is a finite element, and algorithms are iterative solvers, etc. So you have to know many components to run finite element method. But I believe you have already learned each of these in undergraduate and high school classes. And so the theory, each of the theory itself is not so difficult. Okay, so this is a road to parallel programming, so parallel scientific programming. So I think we have 4 steps. First one is you need to know the Unix, Fortran, C, etc. So it's a so-called a very fundamental literacy. So next one is the programming for fundamental numerical analysis, such as Gauss-Seidel, Runge-Kutta, etc. I believe many of you have already done this. But after that, so you need to do some programming for real-world scientific computing using finite element or finite difference. And the programming for parallel scientific computing is the next step. Okay. So basically, so these 2 parts are not usually taught in university of courses. Okay. So it's the same situation in Japan. And so usually we have a big gap here between the very fundamental programming and the real world programming. Okay. So if you don't know the detail of the programming for the real world applications, you cannot do the parallel computing, even if you know the MPI or OpenMP. So I think this third and fourth steps, especially third one, is very important. And this class is starting from this third one, based on, so you are already familiar with the first and second ones. Okay. Okay. So as I mentioned, this third step is very important. And so as I mentioned, so if you know how to parallelize the applications, and you need to know how to extract parallelism. And if you understand the method, algorithms, and implementations of the original code, it's easy. Okay? So data structure, which I mentioned in the beginning of this class, is very important. So how to understand the code? So the best way is reading the application code. Okay, so you just go reading. Okay, so it seems primitive but very effective. And in this class, reading the source code is encouraged. So I believe you have already browsed some of the materials in this class, and you can see many parts showing the codes and so providing some explanation in details. Okay. Generally speaking, the lectures in scientific computing is just teaching the theory. But in the case of the programming, so we need to write the proper code. Okay? And so it's very difficult to write proper code without any examples. And I hope this class will provide such ones. I don't say my code is the best one, but so I think it's probably show you some ways in the future. Okay, so I'll just briefly overview the procedures of the finite element method. So how many of you have learned about finite element method before? Any persons? Oh, okay. Thank you. Okay, so finite element method is one of the most popular numerical methods for solving PDEs. So PDEs stands for the partial differential equations. Okay, and we have two components, elements and nodes. So let's consider this 2D heat transfer problems like this way. And the lambda is a heat conduction. So this large T is temperature. And the Q is a heat generation for each element. So you can see we have 16 nodes, 9 bilinear quadrilateral elements, and the uniform thermal conductivity, lambda equal 1, and the uniform volume heat flux, Q equal 1. So we need a boundary condition. And so we fix the temperature at the point 1 equal to 0. And so it's insulated boundaries for the other part. So this is our current target problem. So we need to apply the Galerkin procedures to each element where T equal N phi. So phi is a temperature at each vertex. N is a shape function. It's an interpolation function. So I'll talk about this this afternoon probably. Okay, so this is the integration equations. And I introduce the weak form of the original PDE using Green theorem. So we can transform these equations to this way. Okay. And we apply the integration to each element and form the element matrix here. Okay, so we have 4 vertices for each element, and its quotient matrix is a 4x4 dense matrix, and the 4 unknowns and the 4 right-hand side vector. So after that, we accumulate each element matrix to global matrix in this way. Okay? And so resulting matrix is very sparse. So we have many zeros. So D is a diagonal component, and X is so non-zero orthogonal components. And the white part are all 0. Okay, so this kind of matrix is called sparse matrix. So if you think about this number 7 element, so number 7 node, sorry. So it's surrounded by 4 elements, and it's connected to these nodes. Okay, so you can see these 3 are number 2 and 3 and 4. And that's, I think it's better to, yeah, because this point has some delays, so it's better to use this. But 同じか。Okay, so it's same. Okay, I use this. Okay. And these two x's are number 6 and number 8. And these 3 are 10 to 12. Okay, quotient matrix is very sparse and many zeros because they have a contribution from only neighbors. Okay, so we need to solve this linear equations under certain boundary conditions. So you remember the temperature is equal to 0 at the number 1 point. So we apply these boundary conditions. Then we get the solutions. So this is a result. And you can see the temperature is 0 at this corner. And according to the heat generation, it's getting so temperature is higher and higher. And at this diagonal, the opponent point, we have the maximum temperature. So this is how the finite element procedure works. Yeah, we start with the PDE and applying some integration for each element and accumulate that matrix and apply the boundary condition and solve that equations. So that's it. So it's very easy. Okay. And so in the following several hours, so I'll talk about more detailed procedures in that. So this is a very brief overview. Okay. So any questions so far? Okay, let's go. Features of the finite element applications is we have several typical procedures: input, output, matrix assembling, linear solvers for large-scale sparse matrices, and most of the computation time is spent for matrix assembling and solving linear equations. So generally, more than 90% is spent for the linear solvers for large-scale sparse matrices, especially in this type of the linear case. Okay. And from the viewpoint of the computations, it's a huge indirect accesses, and it's a so-called memory-intensive applications. And it's based on the local element-by-element operations, and that's why we have a sparse quotient matrices. And this type of the procedures is very suitable for parallel computing. Okay. And excellent modularity for each procedures. And so you can use each component to other applications easily if it's based on the finite element method. So this is very widely used method for the real-world computations. Okay, so next part is the supercomputers and computer science. It's a very general issue. Okay, you are already familiar with the computer and CPU, and the CPU stands for the central processing unit. And the CPUs used in PC and supercomputers are based on the same architecture. And so this time you are using the ARM-based A60FX on our supercomputers, and so it's designed for the special purpose of the high performance computing because the PCs is doing many types of works, and so it's a little bit different, but based on the same architectures. Gigahertz is a clock rate, and it's a frequency, and it's number of the operations by CPU per second. And the gigahertz means billions of operations per second. So it's a very huge number. Okay, so recently, most of the CPUs are based on the multi-core CPU architectures. in the previous century, before year of 2000, mainly, so the CPU was just with a single core. But so at the beginning of this century, dual core architecture appeared. And now, so it's getting more and more. Okay. And the core is a central part of the CPUs. And so original motivation for the multi-core CPU is a low power so consumptions. But so if you have a multi-cores, so each core can do so different works. So in the case of the PC, so some of the cores is working for the word processors. So others are PowerPoint, and another one is going to so just controlling the screen. Okay, so it's very possible. But in our context, we are utilize these multi-cores or many cores for parallel computing. Okay, and the GPU is also popular for so the computing, and it's actually it's more than 100, nearly 1,000 cores. So they are doing the so graph processing unit, but it's a kind of the many core. Okay, so this time, so you are using this Wisteria BDX Odyssey. So in this case, we have 48 cores per node, and you need to utilize these cores simultaneously in parallel manner. Okay, so GPU is very popular, and the GPU is originally a graphic processing unit. And so in recently, so they have a general purpose GPU. So it's focusing on the computations, not the graphic processing. Okay, and so actually order of 100 or 1,000 cores. And the original motivation for utilizing GPUs for the scientific computing is a high memory bandwidth. Okay, so it's very nice to handle the large scale data. That was cheap before, but now it's very expensive. Okay, and so they cannot do the so standalone operations, so they need a host CPUs. Okay, and the programming is a little bit different and from the CPU and the CUDA or OpenCC, etc. But recently, programming environment is has been dramatically changed, and it's much more easier than before now. Okay, and also NVIDIA is the only company, so they which produce GPUs. But as you may know, so we have other companies such as AMD or Intel also developed their own GPUs. Okay, GPU is not the so target in this class, but so yeah, it's a very important devices. And all of you know about so GPU is very useful for the machine learning or so AI type applications. Okay, so this is the parallel supercomputers. Multi-core CPUs are connected through network, and so there are some heterogeneous or hybrid nodes. So using these GPUs. Okay, so next I'll talk about the performance of the supercomputers. And so as I mentioned, clock rate, gigahertz is very important. And another criteria is flops. Flops stands for the floating point operations per second. It's a real number. Generally, it's a double ratio. Okay. For example, so if you have 4 or 8 flops per clock in the recent multi-core CPU, so that means so during a single clock, they can do the 4 to 8 operations simultaneously. Okay. So in that case, peak performance of a core with 3 gigahertz is 3 by billion by 4 or 8, and it means so 20 or 24 gigaflops. Okay. And 10 to the 6 flops is 1 million. It's 1 megaflops or 1 M flops. Billions is a giga or G flops. and 10 to the 12th is teraflops or T-flops. And the petaflops and exaflops, so is every 1,000 times. So actually, the current supercomputer, fastest supercomputer in the world is the order of the exaflops. Okay, so this is a Wishtera VDEX which you are trying to use in this class. Okay, so I'll talk about this later in detail. And we have two types of the node groups, and so you are using this simulation nodes called Odyssey. Okay, so we have so A62FX processors, and we have so nearly 8,000 nodes, and the core number is so 368,000, and 26 petaflops. Okay, it's a commercial version of the Fugaku. So we have another part for the GPU cluster, but so this time we don't use this part. Okay, so this is a very brief overview of the A64X processor on Odyssey. So it's each CPU. So we have 4 CMGs. CMGs stands for core memory group. And each CMG has, so this HBM2 is a local memory, and 12 cores per CMG. Okay, and it's a 2.2 gigahertz, and 32 double precision computing in a cycle, and we have 48. So that means 33,000 gigaflops. So that stands for the 3.38 teraflops. It's a very fast system. And it's based on the NUMA architectures. NUMA stands for the non-uniform memory access. And each core of each CMG can access the remote memory, but it's not efficient. And so we try to utilize local memory as much as possible. Okay, so next topic is the top 500. So it's a ranking list of the supercomputers in the world. And if you are interested, so you can access this homepage. And the performance is a props rate is measured by a RIMPAC, which solves the large-scale linear equations. It's a very simple benchmark. And so it started in 1993, 40 years ago, and updated twice a year. So we have international conferences in June and November in Germany and USA. And this June, yeah, precisely it's so May, so it's updated. Okay. So Fugaku has been #1 from June 2020 to November 2021, 4 times. And the Frontier is the first exaflop system in June 2022, last year, and now it's still the #1 in the world. So RIMPAC has an iPhone and Android version is available. And so if you are using a smartphone, yeah, in the case of the iPhone, if you visit the Apple Store and search the RIMPAC, so you can easily find that. Okay, so this is the history of the top 500, and we have 3 lines here. Okay, so this center one, yellow triangles, shows the performance of the #1 system, and this so blue diamonds show the performance of the list, number 500, and the green one is the sum of these 500 systems. Okay. And you can see, so there are some flat line here. Okay, so I think this one is a Earth simulator, so in Japan, and so this one is I don't know where. So this is some Chinese systems, and this one is a K computers, and this one is a Fugaku. Okay, and so the fastest system now is so over exaflops. So this is the most recent list. You can see, so top is a Frontier in USA. So second is the Fugaku in Japan. And the third one is a Lumi system in Finland. So basically it's operated by EU funding. Okay. And our system, with stellar BDX Odyssey, is the 25th in the world. Okay. And number 3 in Japan. Okay, so this is a link back on my iPhone. So my iPhone is a little bit old, 4 years old. It's a XS. Okay, now it's a version 14 or something, and it's much faster than this. Okay, so if you check the performance of the iPhone by link back, so you can get the several performance. So you have the normal mode and the low power mode. And generally speaking, low power mode provides a lower performance. You can see, so this is a megaflops rate, and it's 8,000, and this one is 11,000. It's almost half. Okay, and so you can also change the number of cores. Okay, and this one is a single threaded, and so top one is a multi-threaded. And you can see, so in the case of a single threaded, performance is 1/4 or something like that. So actually, the performance is my iPhone is so this one is a 20 gigaflops, okay, 20,000 megaflops, okay. And when I entered the company after graduation of my university, so more than 35 years ago, 1985. My company owned a supercomputer. It's called Cray 1S. The peak performance was 80 megaflops. Okay, so you can see if you compare with my iPhone, it's much slower. Okay, but at that time, it's one of the fastest supercomputers in Japan or in the world. And I don't know the price of the system, but we had to pay 10,000 US dollars for 1 second of the computing. Okay, so it's a very expensive. Okay, so anyway, so this is very much advanced. Okay, so anyway, so you can test your smart home by this impact. It's very interesting. Okay, so actually this impact is not practical benchmark anymore, and we have other types of the benchmarks. So HPCC, so it's a preconditioned iterative solvers. It's very similar to our applications. Okay? So it's measuring the performance of the real applications. Okay, so this is a very brief overview of the hardware of the supercomputer. Okay, so any questions or comments so far? Okay, so next part is about the applications. Okay, so utilization of the supercomputers. Okay. For a long time, we have two pillars of the science. It's the theory and experiments. So theoretical and experimental sciences are the two pillars of the science. But so in 1990, okay, so 30 years ago, we have a third pillar. So it's a computational science. It's a simulations using supercomputers, like this way. Okay, and so some people say that data science is a fourth pillar, but it's not so popular as this third pillar. Okay, so anyway, but so simulation is now very widely used in the actual science. We have many methods for scientific computing. And so one typical method is numerical solutions of the PDE, partial differential equations. So generally speaking, this type of approach uses some mesh, grids, and particles, like the finite element, finite difference, finite volume, or boundary element, or some discrete element method using these particles. So generally speaking, so you need to solve the large-scale linear equation, which I mentioned in the brief overview of the finite element method. And generally, if we apply the finer meshes or more particles, so we can get the more accurate solutions. But we need so more computational resources. Yes, that's a big problem. Okay, so I'll show you some examples. One is the 3D simulations for earthquake generation cycles. It's a San Andreas Fault in California. So we actually, I remember this morning we have some earthquake here. Is that right? Mm. Yeah, it's also very usual in Japan, but so yeah. I saw many people from Europe in my hotel. Probably they are very scared about that. Okay, but anyway, so this is some earth science applications, and in this case we have some so fault here, and we have some stress accumulations, and we apply the very fine mesh, and actually, so if you are away from the this so fault, we don't need the fine meshes, and we can utilize this type of the adaptive mesh. So this is a typhoon simulations by finite difference method, and yeah, you can see. So yeah, these are the mesh size, and the effect of the resolution is very clear. So next one is the simulation of the geological CO2 storage. Okay, so as you know, CO2 is one of the most famous greenhouse gas, and it's very effective for the global warming. Okay. So reducing the CO2 is a very critical issue for the sustainable future. Okay. So there are many methods. Okay. So one of the methods is trying to not to use the oils or coals, and one of these approach we have tried to put this type of the CO2 underground. Okay, so this type of approach is done by a construction company in Japan. So this slide is borrowed from my friend, Dr. Yamamoto. He's working for the Taisei Corporation. So this is internationally and interdisciplinary collaborations, and Taisei and Lawrence Berkeley and our computer center and Jamstack and NEC for the science, modeling, algorithms, and software and hardware. Yeah, it's many years ago, but we received the Japan Geotechnical Society Award. So science is the behavior of CO2 in supercritical state at deep reservoir. Okay, so it's a very complicated physics. And the PDE is also very complicated. It's a 3D multi-phase flow, liquid and gas, plus a 3D mass transfer. It's a nonlinear PDEs. Okay. And the method for computation is a Tufts code based on the finite volume method and developed by Lawrence Berkeley National Laboratory, USA. Okay. And more than 90% of the computation time is spent for solving large-scale linear equations with more than 10 millions of unknowns. So as for the numerical algorithm for solving this type of the equations, linear equations, so we developed the first algorithm for large-scale linear equations developed by ourselves. And the supercomputer is an Earth simulator in Jamstack by NEC, and also our supercomputer. Okay, so this is a how the CO2 is so absorbed into the groundwater. So we are using the coarse mesh and fine mesh. And you can see the amount of this absorbing is very different using the coarse and fine mesh. And usually we need a very fine mesh. Okay. And this is a more 3D phenomena. And this type of application, we need to solve the very long time. In this case, it's 10,000 of years. And so we need to solve the large scale problems. And also huge number of the time step. It's so 100,000, like this way. Okay. Okay, so this is a result. It's just a scalability. Okay. So this axis shows the number of processors, and this one is a computation time. So generally speaking, if you increase the number of the processors, you have a smaller computation time. But you can see, so it's saturated at certain point. Okay, so you will experience the same type of the issues during this class. But you can see at so around the 10,000 processors, so computation time is larger. Okay, so this means so if you increase the number of processors, so you need more time. Okay, and the performance is saturated here. Okay, so this is the original code. And this is a result by our solvers. And generally, so the performance is 2 or 3 times speed up. And also we have a very nice scalability here. Okay? And by this way, so yeah, total performance as a 10,000 processors are 5 or 6 times larger. And yeah, it's very nice for the so efficient computations. Okay, so I think it's a good point to stop because it's 10 o'clock and we have a 10-minute break. And please come back at 10 past 10. Any questions? Okay. Okay, thank you very much. Okay, so let's go to the next part. Okay, so this page shows just repeating the same words and so motivation of the parallel computing and so some scaling issues. Okay, so I'll talk about the overview of the class. And so instructor is myself. And so this is my email address. And yeah, you can directly send email, especially after this class. Okay. And the schedule is this week, 9:10 to 5 o'clock. And the homepage is here. And so we have some practice. So this is a prerequisite knowledge and experiences in fundamental methods for numerical analysis, and so such as Gaussian elimination or SOR or something like that. And the knowledge and experiences are Unix and Linux because so in the supercomputer, so you need to know about Unix, Linux. So yeah, that's why this is a requirement. And so, yeah, I just show you some such kind of the web page to run these things. So, especially you need to run about the editor, VI or Emacs or something like that. And the experiences in programming using Fortran or C. Okay, so how many of you are familiar with Fortran? Okay. 2. How about C? Okay, so C is a majority. And actually, so I have prepared the 2 materials for Fortran and C. And so I'll just provide so presentation on the screen by C language material. But so yeah, you can learn by the Fortran material because they have exactly same page configurations for C and Fortran, and you can easily catch up. Okay, so this is a schedule, and hopefully I can finish before 3 o'clock on the Friday, and so but it's up to the advancement. Yeah, there are many books for the finite element method, And so this one, so Fish Belichko's book, so it's a little bit old, and so Abacus student version is included, and yeah, you can learn about so finite element analysis very easily. And so programming the finite element method is so focusing on the finite element method programming. But so these guys are from the civil engineering, and so the program is yeah, mainly focusing on the such kind of applications, such as soil mechanics or something like that. But yeah, you can learn the programming. And this one, Tom Hughes, the finite element method, and the linear and static dynamic finite element analysis, it's a very well-known textbooks. And you want to run, if you want to run the finite element for the more fundamental part, so you can read this. Okay, so there are some future issues. So it's so future issues for the high performance computing. Power consumption is a very critical issue. And as you know, so energy cost is now getting higher and higher all over the world. And if you have larger systems, reliability and fault tolerance and fault resilience is almost also the critical issues. And the scalability, parallel performance is of course the important issues. So Jack Dongara, so he's a very big name in the world of the high performance computing. He's one of the organizers of the top 500, which I mentioned before. And he mentioned about the key issues towards the applications and algorithms on exascale systems. Okay, so now we are in the exascale era, and he mentioned about that 10 years ago. Okay, and hybrid and heterogeneous architectures and multi-core plus GPU or many cores, and yeah, data movement and hierarchy of the memory is important. So it's true. Okay, communications and synchronization, reducing algorithms. I don't get into the detail in this class, but so it's still a very important research topic. So mixed precision computation is also important, and auto-tuning, self-adapting, and fault-resilient algorithms, and reproducibility of results. So the current supercomputer is still reliable enough for reproduce the same result. But so in the future, so we need to think about the reproducibility, the result. Okay. So yeah, for example, the quantum computer, so they have so big errors, and results by quantum computer themselves are not reliable now. But we try to somehow understand what is happening. So in that case, we need a different point of view. But so this time, so we are assuming the reproducibility of the results. Okay. Okay, so this is the end of the introduction part, and I just briefly overview the supercomputer and parallel computing, and also finite element and computational science using the supercomputers. Okay, so any questions for this part? If not, so let's go into the introduction to the finite element method. Okay. Okay, so let's start with the finite difference method and finite element method. So how many of you have learned finite difference method before? Okay. Oh, most of you. Okay, thank you. So both of them are solving the method for the numerically for the partial differential equations, PDEs. Space is discretized into small pieces, elements or meshes or grids. Okay. And the finite difference method, FDM, is a differential derivatives are directly approximated using Taylor series expansion. So it's more mathematical. Okay, so let's so think about this 1D geometry. So with the equally spaced, and the phi is some so independent variable. So these two are the Taylor series expansions around phi I. So phi I plus 1 and phi I minus 1 is so described in this way. So if you take the difference between these equations and divide it by 2 delta x, you can get this equations. So you can see, so we have a different signs here, and for example, this even number order terms are cancelled if you take the differences. Okay, and so you can see phi I plus 1 minus phi I minus 1 divided by 2 delta x is equal to first order differentiation of the phi and higher order values. Okay, so because the delta x is very small and the delta x square is very small. So this means so this type of the higher order part is almost negligible. So in that case, it's neglected. But actually, so we have a finite value of errors, delta x square. Okay? And so this type of the approximation is a second order approximation because the highest order is so largest order is a delta x square. And sometimes it's called the second order central difference. So in order to describe the first order derivative of phi at point I. Okay. Yeah, basically, so finite difference method is also considered as a macroscopic differentiation from other point of view. Okay. So if you think about these 2 points, and so distance is delta x, and try to calculate the first order differentiation at this center point. So you can easily get the idea that so this is equal to phi I plus 1 minus phi I divided by delta x. Okay, and if the delta x is really close to 0, so it's a real first order differentiation. So it's based on the definition of the first order derivative. Okay, so because the first order derivative or first order differentiation is equal to the gradient of the this part, and yeah, it's very easily understood, I hope. And how about the second order differentiation? Okay, so you see at this I plus 1 over 2, so it's defined this way. Okay, and if you want to calculate the second order differentiations at I, so you just differentiate the first order differentiation at I plus half and I minus half. Okay, like this way. Okay, and I plus 1 half is this way, and I minus half is this way. And finally, so you can get the result here. Second order derivative or second order differentiation at I is phi I plus 1 minus 2 pi I plus pi I minus 1 divided by delta x square. Okay? So I believe some of you have already seen this before, to how to implement the second order differentiation by finite difference method. Okay, so please keep in mind, okay, keep this in mind. Okay, so in the case of the 1D heat conductions, because in this class we are targeting the heat conduction problems, it's a second order partial differential equations. Okay, and we need to utilize this second order central difference. Okay. So this is the 1D heat conduction problem. And if you discretize this in the finite difference method, so this type of equation is obtained for each mesh. Okay, and so if you combine these equations, it leads to the they lead to the a single big equations. So it's a linear equations, and we need to solve that. Okay. So this is a very brief overview of the finite difference method. And the finite element method is a little bit different way. Okay? It solves the weak form derived from integral equations. And the weak solutions are obtained. So yeah, if you solve the problem directly, it's called strong solutions. But basically, weak solutions and strong solutions are same. Okay? And the method of weighted residual or variation method are used. And it's generally suitable for complicated geometries. Although finite difference method can handle complicated geometries like this way. Okay? Yeah, even for the case of the very structured finite difference method, so if you apply some curved boundary, it's called a BFC. BFC is a body fitted coordinate system or something like that. So you can discretize this kind of the very complicated turbine model in finite difference mesh. But generally speaking, finite element method is more suitable for complicated geometries. Okay, so I just briefly talk about the history of the finite element method. It's not so old. So it started in 1950. And so, yeah, I think it's an era of your grandparents. Okay? And the finite element was originally developed as a method for structure analysis of the wings of airplane and the collaborations between Boeing Company and University of Washington by Dr. Turner and Martin, etc. Actually, so Boeing is a very well-known aircraft company, and its headquarters is in the suburb of Seattle. So Seattle is home of the University of Washington. So it's a very local collaboration. So as you know, before World War II, aircraft used the so-called reciprocal engine. So they are using the propellers. Generally speaking, they are not so fast, and they are using this type of the wing. It's perpendicular to the body. Okay. So this is very nice for getting the force. But in the case of the transonic or supersonic aircraft by jet engine after World War II, so it's not good. So mainly for some aerodynamics problem, they need to adopt this type of the swept back wings. Okay? And wing is a very important component of the aircraft, and they keep the force for the flying, and also they are storing the fuels. Okay, and so this part, so the root of the wings, they have a very big force during the flight, and so trying to design the strong enough wings is a very critical problem. But generally speaking, if you want to get a strong wing, you need to put more metals. But it provides a heavy aircraft, and the performance is not so good. So designing the aircraft is very critical. Okay, so you are mainly from the natural science, and so if you are from the mechanical engineering, they have some safety parameter. Okay, safety parameter is think about the highest force. Okay? Usually, that type of the parameter is a 5 or 10 in the case of the mechanical engineering, such as a car or building. But in the case of the aircraft, it's 1.3 or 1.4. That means we just design the aircraft just 30% or 50% larger than the ultimate force. So it's a very critical. And before World War II, we can utilize the beam theory to design this type of the wing. But so in the case of the swept-back wing, we cannot apply this beam theory. So that's the reason why we need a numerical method for solving this type of problems. So that's the origin of the finite element method. Okay, so it's very clear. And it started from the solving the linear problems for the structural mechanics or solid mechanics. But it was extended to various applications in recent, almost 70 years. Professor T.J. Oden developed a nonlinear approach, and Oshi Tsinkevich extended that method for the non-structure mechanics, such as fluid mechanics or heat conduction or groundwater flow. And another reason for the very important issues for the finite element is they have a commercial package called Nastran. Okay, so Nastran was originally developed by NASA for designing the aircraft and rocket. But so they opened the source code in very early stage. I think it's before 1970. Okay, and many commercial versions were developed based on these source codes. And most famous one is by MSC. MSC stands for the McNeil Schwendler Company in USA. And 30 years ago, so they developed the PC versions, and it's widely used in the industries. When I entered my company, Nastran only worked for the supercomputers at that time. But so after 6 or 7 years later than that, so PC version appeared, and it's widely used now. And most of the designing, especially in the mechanical and the car and aircraft, so they are using Nastran. So recent research topics, actually it's not so recent, but nonlinear problems such as crash and contact and nonlinear materials are very important issues. Parallel computing is also important. And adaptive mesh refinement is very useful for the shock, wave, and separations, stress concentration. But dynamic load balancing of our parallel computing is a very critical issue. And another important point is the mesh generations. It's not a solving part, it's a processing part. So this is also still a hot topic for research and development. Okay, so I have already shown this about earthquake generation. And so I think it's already shown. I just show you the video. Okay, so this is a supersonic flow around the sphere. And we start from the very coarse mesh. And so it's a small number of grids. But if you apply the adaptive mesh refinement, so we have a small mesh here, and we can resolve the this kind of discontinuous change of the. In this case, it's pressure. Okay, and in the parallel computing, we have a imbalancing like this way, and so we need to do the balancing this way. And another level adaptations, we have another very huge imbalance. And also we can balance this load in this way. So this type of method is very important in the utilization of the parallel computing to the real world applications. Okay, so this is a very brief overview of the history of the finite element method. Okay. So next part is a little bit mathematical part. First, we start the numerical method for solving the PDE. Okay, and the method of the weighted residual. And after that, I have a very short chapter for the Green and Gauss theorem. And after that, also we have a numerical method for PDE using the variational method. But in this class, we are mainly focusing on method of weighted residual, and so I don't get into the detail here, but I just show you some examples. Okay, so approximation method for the PDE. So we have many methods, and so let's consider this type of the linear equations. It's a boundary value problem without time-dependent terms. And the domain is equal to V, and the boundary is equal to S. And the U is so independent functions. So LU is equal to F. So U is a solution, and that can be approximated by function of UM. So UM is a linear combination of this phi I. Okay, phi I is called a trial function or a test function. It's a known function of positions, defined domain, and at boundary. It's something like a basis in linear algebra. Okay, and phi is a known functions, and A is a coefficient. And our target is so calculate the combination of AI. Okay, so it's a coefficient. And the number of these terms is equal to large M here. So method of weighted residual, MWR. I will talk about this. So UM is the exact solution of U if R equals 0. So R here is called residual because LU is equal to F, but as long as UM is some approximate solutions, it's not 0. But so our target is trying to minimize this R residual. So in MWR, consider the conditions where the following integration of R multiplied by W over entire domain is equal to 0. So in this case, so we are multiplying W. So W is called weighting function. Okay? And apply integration over the domain, and it's equal to 0. And what do you mean by this? Something like this. Okay? So this method is not trying to provide the R equals 0 condition. And so this is R is so this type of some distribution in the 1D problem. And so yeah, MWR provides a smooth approximation solution which satisfies R equals 0 in the domain V. So yeah, in other words, so average of R of the each point is 0 in the case of this method. Okay, so that's the approach of the MWR. Okay, so in the MWR, the selection of the interpolation function and also this weighting function is very important. On the contrast, we have another approach called variational method. So it is widely known that exact solution of U with extreme values. So generally it's maximum of functional IU. So Euler equation is a differential equation satisfied by U if functional has extreme values. And the Euler equation is satisfied if U provides extreme values of IU. Okay, and providing the extreme value is something sometimes called stationarized. So for example, functional, which correspond to the governing equations of the linear elasticity, principle virtual work equilibrium equation is principle of minimum potential energy. Okay, so basically, if we consider some governing equations, functional is corresponding to some energy theorem. Okay. So actually, we can apply the same type of the approximations. So using this type of the polynomials. Okay. And so in this case, we define this IM, which is so this UM is put into the functionals. And so try to find the conditions where the IM provides extreme values. Okay. So variational method is theoretical method and can be only applied to the differential equations which has equivalent variational problem. And in this class, we mainly use MWR. But a brief overview of the Ritz method, it's one of the variational methods, will be given later in this material. Okay. So how many of you have learned about the variational method before? No? Oh, just one. Oh. So actually, I was a student. I learned variational method in the winter semester. So second half of the sophomore years. But in University of Tokyo, they don't teach now. Okay, so no students know about the variational method. It's a very critical issue. But anyway, so even if you don't know that, so I'll talk about the very brief introduction of the variational method later. Okay, finite element method is the entire region is discretized into the fine elements. And so this type of the approximation is applied to each element. Okay? And MWR or variational method is applied to each element, but in this class, MWR. And each element matrix is accumulated to the global matrix, and the solution of the obtained linear equations provide approximate solution of the PDE, which I mentioned in the previous part. Okay, so I skipped the detail of the finite element method here, but I'll talk about more about the MWR and variational method. Okay, so this slide shows a very fundamental examples of the MWR. So we think about the thermal equations, okay? And lambda is the conductivity, capital T is the temperature, and the Q is the heat generations. And the V is the target domain, oops, and S is the boundaries. And the T equals 0 at the boundary S. So it's so-called the Dirichlet boundary conditions. And the T is approximated by these polynomials. And if we this application in the original PDE, so you can get the residual. Okay. In this case, you just put this phi into this T. Okay. Because the A is a some constant, and the phi is a function of the location. That work. You can see, so second order differentiation by phi is obtained here. So this is a residual. And multiply weighting function W and apply integration over V. So this is MWR. So generally speaking, if we have interpolation functions, we need n weighting functions. So number of the interpolation functions and the weighting functions must be same to get the proper number of the equations. So if a set of weighting function W is a set of n different functions, the above integration provides a set of n linear equations. Yeah, as I mentioned, so generally speaking, so these numbers should be same. And so if we just introduce so this R into these equations, you can finally get this equation. Okay. So J is so for these parameters, and I is corresponding to each weighting function, and we have n such kind of equations. So this is a matrix form of the equations, and so B is a quotient matrix, and each component of B is like this way, and I and J are the index, and I is for the weighting functions, and the J is for the interpolation functions. And this is a right-hand side. Okay, so that you can solve this BA equal Q. So actual approach is slightly different from this, but I'll talk about that in the later stage of this class. So this is a very basic approach for MWR. Yeah, probably it's very difficult to understand, and I will show you simple examples. And so we have various types of the MWRs, so based on the various types of the weighting functions. One is the collocation method, least square method, and so last one is Gallatin method. So I'll introduce these three methods one by one. So in the case of the collocation method, weighting function is a Dirac delta function, delta. So definition of delta function is in this way. So delta z is infinity if z equals 0, like this way. Okay? It's a discontinuous function. In other part, so delta is equal to 0, like this way. And the integration of this function is equal to 1. So this is the definition of the delta function. So in this case, weighting function wi is defined as a delta x minus xi. And x is a location. In the xi is a location of the collocation point. In the collocation point method, r is set to 0 at n collocation point by feature of the Dirac delta function, delta. Okay. And if you apply, so this way, r is a residual, and it's multiplied by delta function as a weighting function. And if you take the integral, the result is equal to r at x equal xi. Okay, and xi is so corresponding to the so-called collocation point. So if the number of collocation points increases, r approaches to 0 over entire domain. So that's the method. Next method is the least square method. And if you study the statistics, it's the same approach as the least square method. In this case, weighting function is defined as wi is equal to so r differentiated by ai. Okay, so yeah, it's based on the theory of the least square method. Okay, so IA is equal to R square and so integrations. And in order to so minimize these integrations, and we have this type of the conditions, okay, where the IA differentiated by AI is equal to 0. So if you calculate this right-hand side, you can get so this way. So in this case, R is multiplied by this so WI. So yeah, you can see. So this is so same shape as a method of the weighting residual. So in this case, this function is defined as a weighting function. Excuse me. So it's a so same idea for the least square method in the statistics. So last one is a Galerkin method. It's a very simple. Okay. In this case, weighting function is equal to test or trial function. Wi is equal to phi I. So Galerkin is the name of the Russian engineer and mathematician. So it's yeah, he was born in 1875, and so yeah, he was worked in the early 20th century. So actually, he was so when he was born, Russia was just a Romanov empire. Okay, and he's one of the anti-Tsarism parties, and he was jailed. Okay, and so when he was jailed in this duration, he got a hint of the Galerkin method. Okay, so this is a very simple and smart method, and in this class we are using this Galerkin method. Okay, so I'll show you the result for these equations by the three methods. So this is the governing equation. So it's so-called 2-point boundary value conditions. And we have analytical solutions like this way. So this is the result. Okay. Okay. And let's think about so U is approximated by these equations. And in this case, we have two test functions, phi 1 and phi 2. Phi 1 is x 1 minus x, and phi 2 is x squared 1 minus x. And you can see, so these functions satisfy the boundary conditions, where u equals 0, where x is equal to 0 or 1. And if you use these functions, you can easily calculate the residual according to the partial differential equations. So this is a residual. Okay. So let's apply various types of the MWR to these equations. So we have two unknowns, A1 and A2 here. So this means we need two independent weighting functions. Okay, so in the case of the collocation method, independent weighting function means different collocation point. Okay, so let's think about n equal x equal 0.25 and 0.5. So that means r at this point, these 2 points are equal to 0, because this is a definition of r. So we just put x 0.25 and 0.5, and we have two equations. And if you solve the equations, result is like this. A1 is 6 over 31, and A2 is also 40 over 217. You can see both of them are close to 0.2. Okay, and this is a final result for you. So next case is a least square. In this case, it's a little bit complicated. Okay, so we have two functions, two weighting functions, so differentiated by A1 and A2. So it's a function of x. Okay. In order to calculate these solutions, you need to calculate by hand. Okay, and so I skip the details, but finally you get these solutions. Okay, yeah, these equations can be solved by Excel. So you need to calculate by yourself to use the equations. But if you compare these A1 and A2, so both are close to 0.2. And you can assume the solutions between the least square and collocation method are not so different. Okay, next one is the Galerkin method. And in this case, W1 is equal to phi 1, and the W2 is equal to phi 2. And again, you need to calculate that. And so this is a result. So the A1 and A2 are close to 0.2. Okay, so next page shows the result. And this is the analytical method and the collocation points. So yeah, we have a different collocation point here, okay, combinations. And the least square and the Galerkin method. Yeah, I think it's better to. Okay, so we just pick the 3 points and you can compare the result. And this is the exact solutions. So you can see, so they are generally similar. But if you compare the whole method, you can see this Galerkin method different. Galerkin method provides a much more accurate solution, okay, than other method. Yeah, it's very obvious, okay? So Galerkin method provides the most accurate solutions. So if functional exist, solutions of the variational method and the Galerkin method agree, because result of the functional, so this variational method is some kind of the analytical solutions. And I'll talk about that in the later this material. And so that's why Galerkin method provides the best answer. So many commercial finite element codes use Galerkin method, and also in this class. But least square may provide a robust solution in Navier-Stokes solvers for high Reynolds number. So in this case, we have no functional. Okay. In the case of the Stokes equations, we have a functional, but so Navier-Stokes we don't have a functional. So in that case, Galerkin method is not necessarily the best way. But generally speaking, was a linear and very static problem, Galerkin provides a best answer. Okay, so I'll talk about that why in the later stage. But the reason is a functional exist solution of the variation method and the Galerkin method agree. So that's why Galerkin method is the best method. Okay. Actually, so I have some exercise, okay? And so, yeah. Actually, I have some new method. One is the moment method, where the Wi is equal to x power of I. And another one is the subdomain method, okay? And so, yeah, you can apply these two methods. Actually, results are, answers are on the web page, and you can check that later. And so another method is so another assignment is to compare the results of the collocation method on non-collocation point with exact solutions, and explain the behavior and why the different collocation points. I think you need to do this now, but so if you are interested in, so you can go to the home page. Oops, just a moment. So if you go to the home page of this class, and you can find the finite element, and you can find some examples of homework. Okay, and you can learn about this. Okay, okay, so I'll give you some short time for doing exercise after this lecture, and so you can try this. Okay, so I'll talk about more about the subdomain method. And the domain is divided into subdomains. several subdomains. So in this case, we have two subdomains. And target region is between 0 and 1. And so we divide the whole thing into the two parts. And so weighting function is equal to 1 for the point in Vy, and otherwise it's 0. Yeah, like this way. So we have some points here, and this is a V1, and this is a V2. And in the case of the V1, so W is equal to 1, and in the case of the V2, W2 is equal to 1. So it's some kind of a method like the finite difference or finite volume method. Okay. And in this case, two unknowns or two subdomains. And so subdomains do not share any overlaps. Okay. You can try this. Okay, so any questions so far? Okay, so I think it's 10:95, 59, and it's good to stop here. Okay, we have a 10-minute break, and please come back 11:10. Thank you very much.
Okay, so next part is the Gauss theorem and the Green theorem. I believe most of you are familiar with this, and so Gauss theorem is one kind of the continuity or conservation of mass. Okay, so left hand side is a divergence, and so right hand side is some through each surface. It's a volume integral. On the right hand side is a surface integral. It's a 3D case, and the domain is V and surrounded by smooth closed surface S. And the U and V and W are three continuous functions defined in V. Okay, it's a functions of they are functions of X and Y and Z. And NX, NY, and NZ are so-called direction cosine. It's the outward normal vector N on surface S. The Green theorem is so it's some extension of the Gauss theorem, and the U and V and W are defined in this way: A multiplied by the partial differentiation of B by X and Y and Z. Okay, so if you introduce these relationships into this left-hand side of the Gauss theorem, so you can get these two terms by theory of the differentiations. And if you apply this Gauss theorem in the previous page, in this part, so you can get so this one and this one is equal to the left-hand side, okay, like this way. Okay. And this part is defined by this way, and finally you can write in this surface integrals, where dB dm is a gradient of B to the direction of normal vector of the surface. And finally, you can get this relationship. So right-hand side, left-hand side is A multiplied the second order differentiation of B by X and Y and Z. And the right-hand side is this surface integral, and also this multiplication of the first order differentiation of the A and B by X and Y. So this appears often in the finite element class. So because from the second order differentiation to the first order differentiation is easily defined by this way. And so this Green's theorem is very important in the finite element method. Okay. I believe many of you are already familiar with this theorem. But any questions for this part? Okay. Okay, so this is a vector home, and so yeah, you might be familiar with these. Okay, so next part is a variational method, and this part is not related to the our content for the finite element directly, but so I just talk about this. Yeah, for your some further knowledge about the finite element method. So I have already shown this slide before, and so here I'm describing the Euler equations, which stationarize the functional IU. And so functional is corresponding to the energy theorem. Okay? And so we can also apply this type of the application for the U, and also we can specify some approximate functional IM. Okay, and we try to stationarize this IM. Okay, so I skip this part. Okay, so let's think about the distortive problem. Okay, and here we have the functional here. Okay, and IU is defined by this way. And so V is this geometry, and S is a boundary. And so Q is a known value, so something like the heat generations, and U is equal to 0 at boundary S. So generally speaking, some application with a variational method is given like this way. Okay? So generally, this functional is not so familiar. Equations, and generally, readers are very confused. So actually, 35 years ago, when I started to study the variational method, finite element method, so many of the finite element book was written in variational method, and it started from this functional, not the differential equations. So yeah, I was very confused with that. But anyway, so this is the functional. Okay. So U star is a twice continuously differentiated partial function and minimizes IU. So U star is a target function. And the eta is an arbitrary function which satisfies eta equals 0 at boundary S. And alpha is a parameter. And let's consider the following equations. So U is equal to U star plus alpha eta. And the U star is the target function. So at this stage, this IU is larger than IU star is a necessary condition. Okay? And let's assume the functional IU star plus alpha eta is a function of alpha. And the functional alpha I provides a minimum value if alpha is equal to 0. Yeah, because it's a U star. So therefore, we can get these equations. Okay, where if you differentiate this I by alpha, it's equal to 0. So because it's stationary. And according to the definition of the functional IU, so this equation is obtained. Okay, so from this definition. And in the next page, I just described how we get this result. So this is the original functional, and this is the definition of the U. So U star is the target, and our condition now is here. And so if you differentiate this, first term of this functional by alpha, so this is a result du dx, d alpha du dx. And the du dx is equal to differentiation of this one here. And so you can apply the separate differentiation for the first part and second part, okay, like this. Okay, and if you differentiate the du dx by alpha, because so this is a result, and so the first part is cancelled and the second part remains because so the coefficient is alpha here. And if the alpha is equal to 0, so this term is going to this one, and so this y term is going to this one. And also, as for the last part, if you differentiate by alpha, so q is a constant, and finally, so this is equal to q eta. So that's why, so yeah, differentiation of this one is going to this integration. So if you apply Green's theorem on the first term of this one, so actually, so you can get this function, okay? And so actually, so this is how we apply the Green's theorem. So this is the original functions, and if A equal eta and B equal U star, and this is the 2D so Green's theorem, and so A is eta, and B is U. And you can see, so this, so first two terms are corresponding to this part. Okay, so from this point of view, so you can get these functions. And finally, so this one is equal to this equation. So you can see, you can get that so second order so differentiation here. Okay, so finally you get these functions, and this is the second term. And so these are the some normal vectors. Okay, and at boundary S, eta is equal to 0, and finally, so you can get this function. And so this A is required if this integral is true for arbitrary eta. Okay, so if eta is not equal to 0, that means so this must be 0 because this integration is equal to 0. So this is a final equations which is satisfied by U star, which stationarize the functional. Okay, so this is a very familiar differential equation. So this is the Parsons equation. Yeah, where so this is also the thermal conduction equation where the lambda is equal to 1. Okay. So this equation A is called Euler equations. So it's a necessary condition of U star which minimizes functional IU. So is that U star satisfy the Euler equations? And the sufficient condition is so assume that U star is a solution of Euler equations and A eta is equal to delta U star. So that means so these two differentiation. So if this is larger than 0, so it's a sufficient condition. And you can see, so these two parts are divided into these two parts. So first one is called first variation. Okay, so this one is corresponding to the Euler equation. And the second part is here. And so you can see, if you see inside the integrations, so they are by square. So if it's a real functions, so this integration value is always larger than 0. So this means, so this is larger than 0. And this is also satisfied in the sufficient condition. Okay, like this way. Therefore, the boundary value problem by Euler equation A is boundary condition U equals 0 at the boundary surface. is equivalent to variational problem. Okay? And solving the equivalent variational problem provides a solution of Euler equations. And the Poisson's equations or heat conduction equations in this case, like this way. But so problem is a functional must exist. Okay. Okay, so this is a 2D case. And let's go back to the another 1D case. Okay. So let's think about the functional here. Okay. And the boundary condition is u equals 0 at x equals 0 and 1. So this is a functional between 0 and 1. So let's obtain u, which stationarize the function iu under these boundary conditions. So actually, corresponding Euler equations is this one. So this one is so solved by Galerkin and collocation method and least square before in the previous slot. Okay, so it's the same equation. And this is a so functional. So let's assume the test functions with nth order, so like this way. And it's twice continuously differentiable. And if we increase the order of the test function, un is closer to the exact solution u. So therefore, functional iu can be approximated by iun. And if iun stationarizes, iu also stationarizes. And we need to obtain set of the unknown coefficient A, so which satisfies so this stationary conditions. So I differentiated by A is equal to 0, where K is equal to 1 to N. The previous equation is a linear equations of the so for A1 to An because so yeah, we have a so n equations for k is equal to 1 to n. So if this solution is applied to equation B2, approximate solution which satisfies the Euler equation is obtained. So this is the approximate solution, but stationarized IU strictly. And this type of method using a set of coefficients A1 to N is called Ritz method. It's some part of the variational method. Okay, so let's apply this method to the original functional. And here again we just pick up that two for the functions. So this is a approximate solution of the U, and then we have two unknowns, A1 and A2. And what we have to do is just define the conditions. So differentiation of the I by A1 and A2 like this way. We just input all solutions, and we can get the solutions. Okay, because this is original functions, and this is approximation of the U, and yeah, so this is the inside of this function, and you can get this result. Okay, if you apply this U into this inside, and what you have to do is just differentiate this by A1 and A2 and get the solution. Okay, so this is same, and this is how we differentiate by A1, and this is the condition for this A1, and this is the condition for the A2, and you can see A1 and A2 are the unknowns, and all this part integration can be calculated. Okay, so because they are known functions, and so we are just integrate from 0 to 1. Okay, then you need to solve the linear equations, and this is a resulted linear equations, and this is a result for the A1 and A2. And actually, this result is identical with that of the Galerkin method. Okay, So I just repeat the result of the Garakin method here. So this is the A1 and A2. And yeah, this is by variation method. They are also same. So this is not a coincidence. Okay? And it's a very important point. Okay, so in the next page, so I just show you so why this is true. So this method and the Garakin method is so same for the result. So in this case, okay. So this is the definition of the integration. Functional. And this is how calculate the differentiation by A1 and A2. Okay. And because so U is defined by the linear combination of the A1W1 plus A2W2, because this is the Garakin method. And W1 and W2 are same as the interpolation function. And also, just keeping these original equations, you can calculate the so differentiation by A1 and A2 in this way. Okay. Okay, so yeah, this is a differentiation by A1. And so this part is going to dividing into this way. So the first term and second term. Okay. And the first term is so we calculate in this way by so integration by part. And we have this term here. And so you can see W1 is equal to 0, well, both of the 0 and 1. Okay. So this term is so neglected. So that we can get this part only. Okay. So as for the second terms, we also have this integration at the boundary point. And this is also 0. Okay. And so we have so this right-hand side. Okay. Okay, so finally, so this condition and this condition is corresponding to this one and this one. So where U is equal to A1 W1 plus A2 W2. So thus we can get this function. So you can see, so this is a so Euler's equation, so partial differential equation here. And the W1 is multiplied and take the integrations. And in this case, we are doing that for the W2. Okay, so this is so method of the weighting residual, and in this case, this is a Garakin method itself. Okay, and we are calculating the so variational method, but finally you can get the same equations as we are doing the Garakin method. Yeah, this example is a very special case, but generally, so result of the Garakin method and Ritz method agree if function exists. Okay, and so although Ritz method provides an approximation solution that satisfies Euler equation in strict sense, so therefore, solution of Ritz method is closer to the exact solutions. So this is the main reason that Garakin method is accurate. And so I just spent recent almost 1 hour about so describing the variation method. Probably you don't understand. You don't fully understand. So because if you don't know beforehand, but it's okay. So here, please remember that so this is the main reason that Garakin method is accurate. Yeah, please just remember this. So it's enough now. And if you are interested in the so variation method, so you can study further. Okay? And this relationship in Ritz and Garakin is not correct if functional does not exist. And in these cases, Garakin method is not necessarily the best method from the viewpoint of the accuracy and robustness. Okay? So yeah, this relationship is satisfied in the linear and static cases. Okay, And for example, Stokes flow. Stokes flow is a very slow flow without convection terms. So they have a functional. Okay? So in that case, they can be solved by variational method. But as I mentioned, in the case of the Navier-Stokes, it's nonlinear, and they don't have a so functional. So in that case, we cannot solve. Okay. Okay. So that's that's the conclusion here. And so introduction to FEM part, and the latter half is mainly focusing on the variational method. But you can forget this after this, because in this class, we are focusing on the Garakin method in this class. Questions so far? Okay, so if not, so let's go to the 1D finite element method. Okay, and so it's more practical part. So this is the overview of this part, and so we start from the definition of the problems, and this sparse linear solvers and storage of the sparse matrices are more focusing on the solving the linear equations. And if you took the class, which in this February, these parts are so overlapped. And the last part, I will show you the so details of the program. The keywords are 1D steady state heat conduction problems, and Garakin method, and linear element, and the preconditioned conjugate gradient method. Sorry? Okay. Okay. So this is the target problem. It's a very simple problem, and the 1D steady state heat conduction. So this is the equations, and because we have only one dependent variable, so it's a ODE, not a PDE. Okay. It's a uniform and the sectional area of this 1D part is uniform, and the thermal conductivity is also uniform. And the heat generation rate per volume per time is also constant along this geometry. And then we have two boundary conditions. At x equals 0, T equals 0. It's a fixed temperature. And x equals x max, another point, ending point. So gradient of T is equal to 0. So it's a insulated boundary conditions. So this is a 1D element in the finite element case. And we have an analytical solution for this kind of problem. Okay? And so this is the original so PDE differential equations. And so because Q is a constant, and so this first order part is so minus Q dot x plus C1. And so this delta T is so Q x squared plus C1x plus C2. So according to the boundary conditions, this one and this one, so we can easily calculate the C1 and C2. Okay. So finally, so this is a result. And this is how the so temperature is distributed. Okay. So at so this x equals 0 point, it's equal to 0, and it's going up. And you can see gradient is going smaller and smaller. And at the end, okay, so because it's equal to 0, okay, gradient is equal to 0, this end. And you can see, so it's equal to 0. Yeah, this is a result. So you can easily calculate by analytically. Okay? In this class, we are trying to do this in numerical. Okay, so here, so let's think about the 1D linear element. Okay, so linear element, we have 2 points at both ends, at each end, and the length equal to L. Okay, so in the case of the finite element method, so we have 2 components. One is a node. So node is a vertex. Okay, and the element is some shape. So in this case, it's 1D plus, okay, or bar. So in the case of the 2D, it's a square or triangles, and 3D, the hexahedron or tetrahedron. And we have 2 points, I and J, and the coordinates are xi and xj. And the temperatures are Ti and Tj. And the temperature T on each element is a linear function of x. So it's a 1D linear element. Sometimes it's also called a piecewise linear element. And in that case, T is equal to alpha 1 plus alpha 2x. Okay, like this way. So this is some meaning of the piecewise linear. It's not so physically consistent, but the temperature itself is linear inside each element. Okay? And the temperature itself is continuous at each node, but you can see the gradient is not necessarily continuous. Okay? So that's the definition of the piecewise linear element. So generally speaking, we have 2 components, element and nodes. And we have 2 numbering. So one is a element ID, and another one is a node ID. And as for the node ID, we have 2 types. One is a global ID here from 1 to 5. And another one, one is a local ID. Okay? Because each node has, each element has 2 nodes. And this one is our first node in local, and this one is the second node in local. So this number 2, global ID is 2. So it's a second node on the element 1, and the first node in the element 2. So this is how we define the interpolation. Okay, because T is equal to Ti at x equal xi, and T is equal to Tj at x equal xj. And if you go back to the definition of the T, T is equal to alpha 1 plus alpha 2x. And if you introduce xi, Ti, and xj and Tj, so you can get these equations. If you consider alpha 1 and alpha 2 as unknowns, okay? And we have 2 equations and 2 unknowns, and you can solve these equations. So I skip the details of the process, but you can get the solution, alpha 1 and alpha 2, respectively, by L and X and P. Okay. So actually, in this case, is unknowns. But so according to this method, T can be written as follows, according to Ti and Tj. Okay. This is a definition of the T1 and Ti and Tj, like this way. So these 2 functions, it's some constant multiplied for the Ti and Tj. They are called Ni and Nj. And you can see both of the Ni and Nj are function of the location x. Okay? You can see xj and xi and l are all known values. And x is a location between xi and xj. And so they are Ni and Nj. These Ni and Nj are called shape function. So in the terminology of the finite element method. Okay? Or sometimes it's called interpolation functions. Okay? It's a function of x, and only x has functions, or only location. And the T is equal to the linear combination of the N and T, okay? NITI and NJTJ. So if you go back to the some interpolation function in the method of the weighted region in the previous part, and yeah, it's corresponding to this one exactly. So in that case, phi was called trial function or test function. It's something like a basis in the linear algebra. And this AI is a constant values, and it's unknown. And we can see, so in this case, N is corresponding to this trial function, and the T is a temperature, so it's unknown values. Okay? So our target is trying to calculate these Ti and Tj. Okay, any questions so far? Yeah, actually, so finite element is very simple. Okay? There are some features of the shape functions. Okay? Value of Ni is equal to 1 at one of the nodes in element. And it's equal to 0 on other nodes. Okay? These are the definition of the Ni and Nj. Okay? So Ni is like this way. Okay? Because if you x is equal to xi, xj minus xi is equal to L. So that's why it's equal to 1 here. And so at this xj, so you can see, so this part is equal to 0. And it's a linear function from 1 to 0 in this way. On the contrast, in the case of nj, at xi, it's equal to 0, but at xj, it's equal to 1. And this is a ni, and this is nj. And so this is a typical case. So in this case, we have only 2 nodes on each element, and it's rather easy, but it's also satisfied in the more complicated cases for the quadrilaterals or hexahedral. Okay. But anyway, so this is one feature of the shape function. Okay, so let's apply the Galerkin method to this part. Okay. So this is a governing equations for the 1D steady state heat conductions. And if we consider lambda is equal to constant, so you can write the equation in this way. Okay. And that T is equal to N phi. Okay. So N phi means the distribution of the temperature in each element in the matrix form. So N is a shape functions, and phi is the temperature at each node. Okay? And this is the governing equations, and this is also the residual. Okay? So if you apply the Galerkin method, we multiply the weighting function. Weighting function is equal to the shape function here. Is multiply the residual and taking the integral. So this V is corresponding to each element. Okay? So this is a Galerkin method. So in this case, we introduce 1D Green's theorem. Okay? It's very easy. Okay? A and B here. And so this second order differentiation is separated into 2 parts, okay? Like this way. Okay, so apply this to the first part here, n and t. And here, n is equal to a, and b is equal to t. Okay? And you can divide this into two parts. Okay? So I just change the sequence. So this surface term is here. Okay? And this second term is here. Okay? Like this way. And the t is equal to n phi. And so dt dx is equal to dn dx multiplied phi. Okay? And if you if you remember the definition of the heat flux at each element surface, I mean the heat flow. So Q is equal to minus lambda, so multiplied by the gradient of the temperature. So this is a definition of the heat flow at each surface. And you can see, so this surface integral part is lambda n dt dx. And you can see, so this heat flux appears here. So in this 1D element, V is like this, okay, it's element. And S is boundary between the neighbors. Okay? So these parts are defined by as a S. Okay? And so these two parts are integration for this one. And this part is corresponding to the heat flux through these neighboring surfaces. Okay. So that's the definition. Okay. Does it make sense? So finally, so we can get the following equations. So you can see the second order derivative is divided into this part and the surface integrals. And so yeah, you can see, so this heat flux is defined as this way. And also we have this volume integrals was a Q. And we have these three parts. And this part is corresponding to the heat through surface. And so this part is heat generated in each element. So this is called weak form. Okay? And the original PDE consists of the terms with the second order differentiation, but this weak form includes first order differentiation. Yeah, this is because by the Green's theorem. And the requirements for shape functions are weaker in weak form, and the linear functions can describe effects of the second order differentiation. Generally speaking, most of the, many of the partial differential equations in the real world is a second order. Okay? And if you directly apply the linear shape functions, and you need to differentiate twice. That means linear differentiation of the linear function is constant. And if you apply the second differentiation, it's going to 0. So that means we cannot solve the problem. But if you apply the weak form, so the second order differentiation is going to the first order differentiation plus boundary terms. So in this case, linear function is enough to approximate the behavior of the second order differentiation. So that's why we usually use this weak form. Okay? Yeah, sometimes we use a strong form where we directly discretize the problems. But yeah, weak form is more convenient for many types of the partial differential equations. Okay. Okay, so this is a definition of the weak form. So any questions for this part? Okay. So actually, this term, this surface term is derived from these values there is a relationship with the neighbors. And these terms coincide at element boundaries and disappear. And finally, only terms on the domain boundaries remains. So domain boundary means here and here. Okay? And so usually we cancel these terms inside the equations. Okay, so we still have time. So let's discuss about the boundary conditions. Okay, and I believe you are familiar with the boundary condition itself. So basically, we have three types of the boundary conditions, and in this class, we are mainly using the two of them. Okay, so one is a value of dependent variable is defined. Okay? So it's called Dirichlet boundary conditions or Dirichlet boundary condition, and it's a so the conditions for the weighting function is equal to 0. So it's a very special. Okay? And sometimes it's called the principal boundary condition. So boundary condition is shortened in BC sometimes, or essential boundary conditions. Okay? And in this problem, at x equals 0, we define the Dirichlet boundary conditions. And another type of the boundary condition is that derivatives or differentiation of the unknowns are defined. It's called Neumann and or Newman boundary conditions. It's naturally satisfied in the weak form because this is corresponding to this surface part. Okay, and it's a secondary boundary conditions or natural boundary condition because it's satisfied naturally. And so this secondary boundary condition is defined at the another end of this geometry. Okay, and so Q is equal to lambda minus lambda so multiplied by dt dx, and it's corresponding to the this derivatives or the unknowns. If it's equal to 0, it's insulated boundary condition. So there are no heat flow, okay? Because this Q is corresponding to the heat flow, and if the gradient is equal to 0, it's corresponding to heat flow is 0 at this boundary. So another boundary condition, third one is called Robin's boundary conditions, and it's a linear combination of the first and second ones, okay? And it's called a third kind boundary conditions, and it appears in the electromagnetics. And so, yeah, long time ago, I was involved in some project in the electromagnetics, but so in the case of the heat conductions or structure mechanics, so this type of boundary conditions generally don't appear, except a very special case. Okay. So in this class, we don't consider this Robin conditions. So we just focusing on these two boundary conditions. Okay, so that we can get the weak form is the boundary conditions on each element. K multiplied phi is equal to F. And the K is this type of the integrals. And the F is right hand side. So it's a volume integrals of the Q dot, the heat generations. And it's a surface heat flux. But in this case, because this Q bar is equal to 0, so this part is doesn't appear in this class. And this E means each element, and each element satisfies these equations because it's derived from the integration for each element. Okay. Okay, so I think it's a good point to stop because it's 11:58. And we start from this page. So how we integrate this. Okay. Okay, any questions or comments so far? Okay, thank you very much. And so let's have a lunch break. Okay, so any questions for the contents of the morning session? Okay, so let's start the next part. Okay, so in the previous part, so I just showed you the so this element matrix for each element. Okay, so next part is how we integrate the equations. For that, we change the coordinate system into the local ones because we are applying the xi and xj as a global coordinate system. But so if you move this to the xi equals 0 and xj equals L, so it doesn't change. Okay, and we just move to the local coordinate system like this. Okay, so in this way, it's much easier. And so actually, in the case of the finite element, element lengths could be different for each element. And L is not necessarily the constant. So L is the length of this target element. Okay. But so in this case, we are assuming the L is constant for all over the case. So if you do this, Ni and Nj can be written in the simpler form. Yeah? Ni is equal to 1 minus x over L. And Nj is equal to x over L. So it's very simple. And the first order differentiation of the Ni and Nj are minus 1 over L and L over L, so individually. So because so this first order derivative is just a gradient of each shape function. Okay. Okay, so let's try to do this integration. Okay. So we have two terms, dn transpose dx and dn dx. Okay, so if you apply these each component for each part, and the first one is a minus 1 over L and 1 over L. And the next one is a minus 1 over L and 1 over L. So it's so this one is a transpose. And if you apply the multiplication of these two vectors, so actually, so this one is a 2 by 1 matrix. We have a 2 rows and 1 column matrix. And this one is a 1 column and 1 row and 2 column matrix. So in this case, we can get the 2 by 2 matrix like this way. Okay? And so you can see, so this is a integration over each element. And so instead of dv, it's a dx. And x is from 0 to L. Okay? And so if you multiply these matrix, basically it's a plus minus 1 over L square. Okay? And you can put this 1 over L square outside of the integrations. And A is also constant, and it can be outside of this part. And so if you do this integrations, the value is plus L and minus L in this case. So finally, this matrix is lambda A over L and multiply these matrix. So diagonal components are 1 and off-diagonal components are minus 1. So this is a integration of this. Okay? So finally, we get this matrix. So this is called local element matrix for 1D case. Okay? Make sense? Any questions? Okay. Okay, so next is integration of this volume flux, okay? Volume heat generations. in this case, Q, N, and we just make integrations. So in this case, N is 1 minus x over L and x over L. And if we do these integrations, so I skipped the details. Finally, we can get this vector, QAL over 2 and 1 and 1. So this is a heat generation for each element. Okay? And the Q is a heat generation rate per volume per time. Okay? And the A is the sectional area and L is the length. So AL is equal to the volume of each element. So this means QAL is the total heat generation per time for this element. And it's divided to, and it's distributed to the each local node. And so this is how we distribute the heat generation to each node. Okay. Any questions? Does it make sense? Okay, so this is how we calculate this. And this is the volume heat generations. And also we can calculate the surface heat flux. So if we have some surface heat generation here, we can do this way. So this surface integration can be utilized for this one. So in that case, we have 2 nodes for each element. And this node, outside node, is only node which is related to the surface heat flux. And then we just put the QA here. But in this case, we have no heat go through this node, and this part is not appeared. Okay. So anyway, so if we have any specified surface heat flux at this node, you can specify in this way. Okay, so thus we can generate the K and F, and so E is phi is a target unknowns, and we accumulate these element matrix or element equations, and we can construct the global equations or global matrix. Okay, so K and F, so capital K and capital F are all accumulation of the element matrices and element right-hand side. And this is the final equations, and or global equations to be solved in this stage. Okay, so before going to the details, please download. I believe you have already downloaded the files to your PC, and so try to compile and run the code. Okay. Okay, so please go to your PC, and so just type this xvfemc.tar, and please go to this FEMC1D, and you can find several files. So in the case of the C, you type the CC or GCC blank minus capital O blank 1D.C. And you can get the A.out or A.exe. Probably A.out will be appeared in your file. And please edit this input that. And so yeah, this provides some information for solving the problem. First row, 4 means the number of elements. And in this case, we have 4 1D elements. And that means we have 5 nodes. Okay? And in the second line, we have 5 1.0. So there are lengths of the element, heat generation, and sectional area, and the thermal conductivity. So all of them are equal to 1 in this case. And the next one is the number of maximum iterations for a conjugate gradient solver. So 100 is enough. So generally speaking, so this number must be larger than this one. Okay? And the last one is the convergence criteria for the CG solver. So I will talk about this later. But anyway, so this is how we define the problem size. Okay? And please so compile the code and edit your input data and run the code. And you can get the answer. Okay, so I'll show you that. And you can get some number.
Open battery. But I can have
Yeah, it is working. This will take some time. Please.
Okay, can you hear? Okay, so under boundary element with a fast multiple method, it's a very special case. But anyway, so we have a different type of matrices based on the different applications or discretization method. So next, we will discuss about algorithms for solving linear equations. One is a direct method. Okay, so very well-known methods are Gaussian elimination or LU factorization. So basically, so they are doing the inverse of the matrix, A inverse directly, or doing the equivalent operations. So this type of approach is robust for a wide range of applications and good for both of the dense and sparse matrices. But generally speaking, it's more expensive than iterative methods from the viewpoint of the memory and the CPU. And it's not scalable. Okay, so and the next part is a iterative method. Okay, and yeah, basically, so it's doing the solving the problems iteratively, and starting from an initial vector x0, and the iterative method obtain the final convergent solutions by iterations x1, x2, doing this way. So we just repeat the same iterations. So generally speaking, so algorithms or the iterative solvers are simpler than those of the direct method. We have two categories for the iterative method. One is a stationary method. Okay, and so this is a typical algorithms for this kind of the stationary method. So xk plus 1 is a mxk. So this one is a previous x plus nb. Okay, and the m and n are matrices, and the b and x are vectors. So in this case, stationary method, only x, so it's a solution vector, changes during iterations. Okay, m and n are fixed. And the typical methods are SOR, successive over relaxations, or Gauss-Seidel, or Jacobi method. Okay, I believe some of you have already learned about this method. And so it's very so simple and very easy to understand, and very easy to understand how the iterative solvers works. But it's generally slow and not practical. And usually we don't use these types of methods for the real-world applications. Okay. Non-stationary methods are more complicated algorithms with restrictions or optimization conditions. And generally speaking, it's called Kirillov subspace method. And we have several methods. CG is a conjugate gradient method. BiCG stub is a biconjugate gradient stabilized. GMLS is a generalized minimal residual. So generally speaking, in the case of a non-stationary method, we use these shortened name. Okay. Conjugate gradient is a long history, more than 70 years. And BiCG stub is developed early 1980s. And GMLS is early 90s. So they are 30 or 40 years old. Rather new algorithms. So if you compare the iterative method with direct method, they are less expensive than direct methods, especially in memory, and suitable for parallel and vector computing. But bad news, the convergence strongly depends on the problems, boundary conditions, or more mathematically, condition numbers of the matrix. And the preconditioning is required. And this is a key technology for parallel finite element method. So fortunately, the applications in this class, so they are well-conditioned problems and are easy to be solved. And we don't need to apply the very sophisticated preconditioning method. But preconditioning is generally very important for the solving the real-world problems. Okay, so next, I'd like to briefly describe the non-stationary or Kirillov subspace method. Okay. So we are solving the Ax equal b, and you can change these equations into x equal to b plus I minus a x, and I is an identity matrix. Okay, and so this x and this ix is same. Okay? And the compute x0, x1, x2 to xk by the iterative procedures. And the xk, so this left-hand side is equal to b plus I minus a xk minus 1. So actually, so if they are converged, so these values are same. Okay. So if you just change the form here, finally, so you can get the b minus xk minus 1 plus xk minus 1. And this b minus xk minus 1 is defined as rk minus 1. Okay? And this is called residual vector. Okay? So if the xk is the exact solution, so this residual vector is equal to 0. So this means the current result is the sum of the previous result and the previous residual. And if you apply this relationship recursively, you can go back to the initial vector. Okay, and you can see xk is equal to initial vector and the sum of the all residuals for all iterations. Okay, so if you do the iterations, you can just add the residual, so you can get the current solutions. Okay, so R is equal to b minus x, And this x is equal to rk minus 1 plus xk minus 1, okay, using this relationship. And that means so b minus axk minus 1 minus a multiplied by rk minus 1. And you can see, so this part is corresponding to the rk minus 1, okay? And finally, rk is equal to I minus a multiplied by rk minus 1, okay? So I is the identity matrix, and a is a coefficient matrix. And you can see, so we can get the relationship between the residual and the previous residual. Okay, so again, so you can apply this relationship recursively, and because xk is equal to x0 plus sum of the residual, and so if you apply the relationship in the previous result, so you can get, so xk is equal to x0 plus r0 plus this, so I minus a power of I multiplied by r0. Okay? And if you consider zk as a r0 plus this part, so expect this x0. Okay? So it can be written as this way, so using this r initial residual. So this type of zk is a vector which belongs to kth Kirillov subspace. And the approximate solution vector xk is derived by the Kirillov subspace. Kirillov subspace is a R0, AR0, A square R0 up to the A k minus 1 R0. So that is corresponding to this zk. And because the solution of this type of the iterative method is described by this so Kirillov subspace, so this method is called Kirillov subspace method. Okay, so this is just a theory, and you don't have to remember, keep in mind, but so please remember the name Kirillov subspace and the definition of the Kirillov subspace here. Okay. Okay, so any questions so far? Yes, so I'll talk about the preconditioning later. But so actually, the application in this class, we don't need preconditioning. But generally speaking, it's better to do that. Yes. For example, so the problem in this lecture is very simple problem. So in that case, we don't need preconditioning. But we have any such simple problems in the real world applications. Okay. So yeah, generally we should apply the preconditioning method. Okay. Any other questions? Okay, so next I'll talk about the conjugate gradient method. So this is a method which we are using in this class. Okay. Conjugate gradient method, CG method, is the most popular non-stationary iterative method, Kirillov subspace method. It's for the symmetric positive definite matrices, so SPD. It's just focusing on this type of matrix. Okay? And the definition of this SPD matrix is X transpose AX is larger than 0 for arbitrary X, if X is not equal to 0. Okay? And another definition is all of diagonal components, eigenvalues, and leading principal minors are larger than 0. So leading principal minors are, so yeah, in Japanese it's called this way. And so if you have a square matrix here, you can define the 1 by 1, 2 by 2, 3 by 3, 4 by 4, and up to n by n matrix and its determinants. So the set of determinants are called reading principal minors. Okay. So generally speaking, so matrices of the Galerkin finite element method for heat conduction or Poisson's equations or static linear elastic problems, so they are SPD, symmetric positive definite. Okay, and we can apply the conjugate gradient method. Yeah, it seems so SPD is a very limited range of the matrices, but so many applications are based on this type of the matrix. So algorithm is the steepest descent method. It's a terminology for the optimization. Okay, and the xi is equal to previous x plus alpha p, and the x is the solution, and the p is called search direction. Okay, and the alpha is some coefficient. And so in the case of the conjugate gradient method, solution x minimizes x minus y transpose a x minus 1, where y is exact solutions. And you can see, so this algorithm is utilizing the feature of the this SPD matrix. Okay, and it is obvious. If x is equal to y, so this value is equal to 0. Okay. And so actually, so under this so feature of the coefficient matrix, we try to minimize this value. Okay, for that, so x minus y. Okay, so this is the procedures of the conjugate gradient method. So you can see it's very easy. Okay. So you can see the program later. So it's just a 20 or so 25 lines. So it's very small program. Okay. And so there are several components. And this type of the value, so p or z or x, they are vectors. Okay. And these alpha, beta, or something like that, rho, so they are scalar. Okay. So in the case of the conjugate gradient method without conditioning, so they have only 3 procedures. Okay, one is a matrix vector multiplication, dot product, and DAXP type of computations. DAXP means so AX plus Y type of computations with double precisions. Okay. For example, so yeah, this one, P equals Z plus beta P is a typical so DAXP computation. Matrix vector multiplication appears only once in the so each loop, Q equals AP. And also it appears in the first part, but it's an initialization. And you can see this is an initial residual vector. Dot product appears 3 times. And this one is calculating the norm of the R vector. And if you include this, we have 3 times. Under DAXP, we have 3 times defining P and X and R. So that's it. So they are very simple procedures. Okay. Okay, so I'll briefly describe how we derive these algorithms. Okay. And you can see, so this is an original algorithm for the conjugate gradient method. So we try to minimize this equation. Okay. And we just expand. Okay. And you can get these values. And finally, you can get these 3 terms. But the last part, Y is the exact solution, and the B is the right-hand side, and this part is constant actually. And what we have to do is so minimizing these two parts, and so it's divided by 2. So our target function fx is here. And if we think about the x plus h, we can derive this relationship. Okay. So in the next page, I have a proof for this. Okay. And so in this case, we are also just expanding the equations. And for example, these are HAX and XAH are same, and we just combine this, and finally, so we can get this equations for arbitrary vector H. So as I mentioned before, conjugate gradient method minimizes fx at each iterations, and let's assume that approximation solution is derived in this way. Okay. And so as I mentioned, P is called defining the search direction. Okay, so you can apply this equation into the previous relationship. So H is equal to alpha kp, okay? And if you calculate this, so you can get the equations of the this alpha, okay? So if you want to minimize this values, so you can get alpha is equal to this values, okay? Because this is equal to 0. So in order to satisfy that, alpha must be satisfy this values. And it's a p. So these are the dot product, p and b minus ax, and p ap, okay? And so this p minus ax is defined as a residual vector r, and alpha k is equal to pr divided by pap. Okay, so this is the first relationship. Okay. And also, you can derive the relationship between the rk plus 1 and the previous rk. Okay, because so this is b minus ax k plus 1 and b minus ax. And if you subtract rk plus rk from rk plus 1, and you can get this minus axk plus 1 plus axk. And this difference is, so xk minus xk plus 1 is equal to minus alpha pk, and so you can get this relationship. So this is the second equation. And the next thing we have to do is define the P. P is a search direction. And this part is a very original part for this conjugate gradient method. And the search direction vector K, P is defined by this recurrence formula. And so initial value of P is equal to initial residual. And the Pk plus 1 is equal to Rk plus 1 plus beta multiplied by previous P. Okay. And the problem is how to define this beta. Okay, so before that, yeah, it's lucky if we can get the exact solution y at the k plus 1's iterations. If you do this at the k plus 1's iterations, so next result might be the exact solutions. So let's consider about that. And actually, so apk and y minus xk plus 1 is orthogonal to each other. And I just prove that, okay? Okay, so apk and y minus xk plus 1. And this a is moved to here, so pk and ay minus xk plus 1.
And AY is equal to B here. So this dot product is going to PK and B minus AXK plus 1. Okay? And the XK plus 1 is defined in this way. And so this part is defined as this way. And finally, so this one is a PR minus alpha K APK. Okay? And yeah, so if you divide this two parts, so okay, so this is a dot product, PR and the P multiplied alpha K APK there, and you can get this relationship. And if you go back to the definition of the alpha, so it's defined by this way, and you can see, so this result is equal to 0. So these two vectors are orthogonal to each other. Okay, so because y minus xk plus 1 is equal to alpha k plus 1, pk plus 1. And if you, so if this is satisfied for arbitrary value of alpha, pk plus 1 and apk must be orthogonal to each other. Okay, and the pk plus 1 and apk, so is based on this definition of the p, it's defined in this way. And if it's equal to 0, so beta must be so written in this way. So this is the fourth equation. And so this beta is defined as this relationship where the pk plus 1 and apk are orthogonal to each other. And this relationship so describes that the pk and the pk plus 1 are conjugate for matrix A. Okay. So pk is a searching direction vector, and sometimes it's also called gradient vector. Okay. And the conjugate gradient method is based on the so this feature gradient vectors are conjugate. So that's why we call this conjugate gradient method. Okay. Okay. So here we have all defined alpha and beta, and we can construct the conjugate gradient algorithm here. But you can see, so this is a little bit different from the one which I showed 5 or 10 minutes ago. So you can see the number of statements are so fewer, and yeah, but it's similar, but it's not same. Actually, so this algorithm, original algorithm, is so provides a smaller statements, but so actually, if you write the program, it's longer. Yeah, because so variables are not so well utilized. Okay, so yeah, actually, so keeping the same result, but we can rewrite the algorithm slightly. Okay. So anyway, so this is the original conjugate gradient algorithms. Okay, so I'll talk about some features of the conjugate gradient algorithms. Yeah. So in the previous part, I showed that the pk plus 1 are so conjugate to each other. But this conjugate relationship is so satisfied for arbitrary combination of I and j, where I and j are different. So pi and apj is equal to 0. And so additionally, so following relationships are also obtained for pk and rk. So ri and rj are also equal to each other, and the pr is equal to rr. Yeah, actually, so both of them are very interesting features. Okay, and so among these, so this one is very important. So residual vectors are orthogonal to each other. Okay, so let's consider n-dimensional space. Okay,
So n-dimensional means n unknowns. Okay, and in that case, only n sets of orthogonal and linearly independent residual vector Rk exist. So if you try to find the orthogonal vectors, so in n-dimensional vectors, so you can find only n vectors. Okay? And this means conjugate gradient method converges after n iterations if number of unknowns is n. Okay? Yeah, this is a very important feature. So it assures, for example, if you have a problem with millions of degrees of freedom, the conjugate gradient method converges within millions iterations. But actually, random error sometimes affect the convergence. Okay? So it affects your questions. Okay? And in the case of the very well-conditioned polymers, so this is satisfied. But if the polymer is so ill-conditioned, sometimes residual vector are not orthogonal to each other. If they are not orthogonal, so we can find arbitrary combinations. Okay, so yeah, that's why we have so different cases. Yeah, this is very important features for the conjugate gradient method. So if you go back to the 1D problems, I will show you. So you have already learned the cases for the 4-element case. If you have 4 elements, you have 5 unknowns, but one node is fixed because it's a one boundary condition. So this means we have 4 unknowns actually. And you can see in the case of the 4 elements, it required 4 iterations. Okay. So what happens if it's 100? So you can assume that we need 100 iterations. Okay. And if you do this, so these are the results. So in this case, we need 100 iterations like this way. And what is happening in the 1,000 elements? Okay. Okay, it's a very long lines, but so you have 1,000 iterations. Yeah, like this way. Yeah, in the 1D case, it's equal to the number of unknowns, and it just follows the rule of the conjugate gradient method. Okay. Okay. Okay, so I think it's a good point to stop, and it's 3 minutes past 3. And the next part, I'll briefly so shows up of these relationships. Okay, so any questions so far? Okay, so let's stop here, and we start the class at 10 minutes from now. Let's start. Yeah, I showed you that these two very important relationships. One is orthogonality. So another one is conjugate features. Okay. So these two relationships so proved by using four equations which already appeared in the deriving the conjugate criteria method. One is the definition of the alpha, and the next one is the definition of the residual vector, and P and beta. Okay. So next part, next page shows so these oops, sorry, it's not shared. Okay. Okay, so this is a very busy slide, and actually, so this is proved by mathematical induction. Okay, and so this number shows us how we derive these relationships. So using these equations. For example, so Ri and Rk plus 1 dot product is equal to Ri multiplied Rk minus K APK is by the second equation. It's based on this one. Yeah. So if you just follow these numbers, so you can easily understand these equations. So here I don't follow the whole procedures, but if you are interested in, so you can just read these later. Okay, if you are interested. Basically, you don't need to know everything about that. But so we are using this mathematical inductions, so you can easily get this information. Actually, there are very few textbooks which describe this type of the derivation of the conjugate correct method, because it requires a lot of sentences. And anyway, so if you understand these, so you can easily get the idea. Okay. Just a moment. Okay. And using so this relationship, so you can finally get this very interesting relationship. Dot product of R is equal to PR. Okay. And this is also obtained using this relationship. So finally, we can rewrite the alpha and beta so in this way. Okay. This is the original definition of the alpha, but it's RR divided PAP. And beta is also divided as RK plus 1, RK plus 1 divided by RK. So you can see the product of R appeared here and here and here. Okay? And if you keep the previous, so this dot product, so you can reuse that. Okay? So that the algorithm itself is more efficient than before using these relationships. Okay. So finally, so we get this algorithm which I mentioned in the first. Okay. And the beta is defined by this way, and this dot product is row. Okay. And if you keep the previous row, and you can calculate the beta very easily. And this row is also utilized for calculating alpha. Okay, and yeah, this is a very convenient dot product. Okay, so this is a brief overview of the conjugate gradient method. So any questions so far? Okay, so next part is conditioning. Okay, and So, yeah, fortunately, the problem which we are solving in this class are generally very easy, and it's a well-conditioned problems. But the convergence rate of the iterative solvers strongly depends on the spectral properties. So spectral property is a mathematical terminology. It's an eigenvalue distribution of the coefficient matrix A. And if the eigenvalue distribution is small and eigenvalues are close to 1, so it's easy to solve. In ill-conditioned problems, condition number, it's a ratio of the maximum and minimum eigenvalue if A is symmetric. So that is large. Okay. And so in condition problems, so this condition number is large. And this means, so it's contrast to this eigenvalue distribution is small and close to 1. But in the case of the ill condition problems, so its distribution is very large. The remedy for that is a preconditioning. So a preconditioner M whose properties are similar to those of A transforms the linear systems into the one with a more favorable spectral properties. So this is a idea of the preconditioning method. So M transforms X equal B into A dash X equal B dash, where A dash is equal to M inverse A and B dash is equal to M inverse B. So we are multiplying the M inverse in both right-hand side and left-hand side. So if the M is close to A, as I mentioned, so M inverse is also close to the A inverse. That means M inverse A is close to the identity matrix. So that's the idea. So if M inverse is exactly equal to M inverse, so this is the best preconditioner, but it's a direct method. And the more general way for the preconditioning is A dash X dash equal B dash, where A dash is equal to M inverse M MR inverse. And the B dash is in this way, and the X dash is equal to MRX. And the ML and MR are called left and right preconditioning method. Okay. So this is a definition of the preconditioning method. So this is a algorithm for the preconditioned conjugate gradient solver. So actually, the only difference is here. Okay. We are introducing a new vector z, and in the case of the original method, z is equal to r. But instead of that, we introduce the mz equal r. Okay. So I skip the details of the how we derive this algorithm. So in the slide, I have already written whole things. Okay. And I don't get into the detail here, but if you are interested, so you can just read the all statements. I just read brief overview. Okay. Here, M is equal to M1, M2, and M1 is a left-hand side, and M2 is a right-hand side preconditional method. Okay, and we just change these this way. So because the original matrix A is a positive symmetry definite, that means M1 and M2 are just a moment. Should be keep the feature of the these features. Okay, so I cannot. So actually, M2 is equal to transpose of the M1. Okay? Because they should be kept symmetrically features. And so M1 is equal to X transpose, and M2 is equal to X. Thus, we just calculate this. So under this assumptions, we can derive this preconditioned conjugate gradient based algorithm. Here we need to solve these equations. Okay, And so that means Z is equal to M inverse R. And so this part is a approximate inverse matrix because M is close to A. That means M inverse is also close to A inverse. So ultimate reconditioning method is inverse matrix. In that case, we don't need to solve the iterative solvers. And in this class, we are applying very simple matrix and a simple preconditioning method. So it's called diagonal scaling or point Jacobi method. So in that case, we assume the preconditioning matrix as a diagonal matrix. So diagonal matrix is we just extract the diagonal component of the original matrix. Okay, so it's very easy to calculate the inverse matrix for that. Okay, so more general preconditioning methods are ILU or IC. And they are the widely used preconditioners for sparse matrices for real-world problems. And the I stands for the incomplete, and the incomplete LU factorization, and the incomplete Cholesky factorization. So IC is for the symmetric matrices. So it's some kind of the incomplete direct method. Okay. So our current target matrices are sparse. Okay. We have many zero components. But even if the original matrix is sparse, inverse matrix is not necessarily sparse. So if you try to calculate the inverse matrix, we have many non-zero components. Okay? That means so we have a more expensive computations. So that kind of the components is called fill-in. Okay? So incomplete factorization is so just a control the generation of the fill-in. The ILU0 and IC0, they are without fill-in. Okay? That means the factorized matrices, so factorized matrices are some kind of the inverse matrices. So they have the same non-zero pattern with the original sparse matrices. Okay? But so in this class, we don't use this. Okay? And actually in the February school, I talked about this, so ILU0 and IC0. But this time, so we are using the simpler matrix. So here, M is equal to this diagonal matrix, and we just extract the diagonal component of the original matrix. And you can easily compute the inverse matrix of this type of the diagonal matrix because you just calculate the reciprocal number of the diagonal components. Then you can get the inverse matrix. Okay? So in that case, solving MZ equal R is very easy. And this provides a fast convergence for simple problems. And 1D.F and 1D.C, and also 3D cases, we apply this type of the preconditional method. Okay, so any questions so far? Okay, so I just talk about some mathematical issues, and the next part is more implementation. So storage for the sparse matrices. Okay. So as I mentioned, in the case of the finite element, we have very many zero components. It's a sparse matrix. Okay. And so I believe many of you have learned some very fundamental matrix operations in undergraduate. And probably you learned to store the matrices in Aij type 2D arrays. Okay. But this is not efficient for sparse matrices. Okay. So this type of the storing method is suitable for dense matrices. because the number of non-zero Hutanen components are very small in the sparse matrices. In the case of the finite element, such number is order of the hundred at most in the real world applications. So if you have a number of unknowns is 100 millions. If you store a whole thing, you need 10 to the 16th words. Okay, if it's double precision, it's order of the 10 to the 17th byte. Okay, so this corresponding to the 100 petabyte. Okay, and so you need in this case you need 400 systems of our supercomputers, not the 400 nodes. Okay. So our system has almost 8,000 nodes, and 8,000 multiplied by 400. It's a huge number of nodes. Okay. But if you just store the actual non-zero components, so you need 10 billion words, and this is corresponding to 100 gigabyte. Okay. Actually, so difference between these two is order of million. Okay. And because if you have more unknowns, so this difference is getting larger and larger. Odyssey has a very small memory, just a 32 gigabyte per each node, but only 4 nodes, it's enough. Okay. But we need 400 systems. Okay. And so it's a very big difference. And only really non-zero Hutanen components should be stored on memory. So that's the proper way. Oops. So variables and arrays in 1D.F and 1D.C related to the quotient matrix are like this way. So N is a number of unknowns. So NPLU is the number of the non-zero Hutanen components. So diagonal component is a diagonal component, and the size is n. And the phi is unknowns, and RHS is a right-hand side vectors. So they are all sizes are n. So we have some additional arrays here: index, item, and emad. Okay, so I'll talk about that later. And so we are storing the only non-zero component of the quotient matrix. So using the compressed raw storage format. Okay, so this is how we apply this compressed raw storage CRS to the sparse matrix vector multiply. Okay, so I just briefly talk about this. So diag is a diagonal component, and the index is the number of the non-zero Hutanen components for each row. And item is non-zero Hutanen components with the corresponding column ID. And this is a real component. Okay. So basically, matrix vector multiply is doing the dot product of the each row of the matrix and vector. Okay, but you can see most of the component of each rows are 0. 0 multiplied by something is usually 0. So this means if you try to compute these dot product, you just pick up the non-zero component and pick up from the corresponding component here. Then you can save the memory, and also you can save the time for the computation. So that's the idea. Okay. So you are doing the product, such dot product n times. Okay, and you need order of n square computations. But in the case of the picking up the non-zero Hutanen components, you can save the computation time. Also, for the memory. Okay, so I skip the details here, but so combining these arrays, you can do the matrix vector multiplication. if you are applying this matrix using the 2D arrays, it's easy. You just apply the double nested loops, and the program is very simple and very straightforward. But so yeah, it's a waste of time and memory. Okay, so I'll talk about the implementation of the compressed row storage using this very small matrix, 8 by 8 square matrix. Okay, so it's a random matrix, and you can see several zero components. So using this compressed row storage. Okay, so because this is a materials of a C program, it's starting from 0, okay, and 0 to 7. And this figure describes the matrix in the previous page. And you can see, so this red part, diagonal components, and these are very light blue parts was non-zero order components, and white parts are all 0. Okay. So in this case, unknown number is equal to 8, n is equal to 8. And the diagonal components are defined in this way. It's separated from the other part. Okay. And you can see upper part is a value of the component, and lower part is a corresponding column ID. Okay, like this. Okay, so diagonal components are stored in the 1D array like this way. Okay, so just get aside. And so how to define the old non-zero binary component? And in the case of the CRS format, so we just ignore the 0 components. Okay, and you can see, so matrix is compressed in row direction. So that's why we call this compressed row storage. Okay, so here we are just store the really non-zero ordinary components. Okay, so this number is corresponding to the number of non-zero ordinary components for each row. 2, 4, 2, 3, 4, 2, 4, 4. And we define the index. Okay, so index 0 is equal to 0. So index 1 is 0 plus 2 and equal to 2. And index 2 is a 2 plus 4 and it's equal to 6. So in this way, we just accumulate the number of the non-zero components to this index. And finally, index 8 is equal to 25. So what does this number mean? Okay, so yeah, you are accumulating these values, and this 25 means the sum of the all non-zero components. Okay, and this number, index n, is called NPLU in this program. Okay, yeah, please remember, so NPLU index, and so yeah, in next page I have another arrays, but so this part is very important. Okay, so we have totally 25 non-zero components, and we can provide the continuous number for the non-zero components starting from 0 to 24. Okay, and so this number is a discontinuous ID for each non-zero components. Okay, so let's think about this number free line. Okay, and so index 3 is 8, and index 4 is 11. Okay, and if you see the ID for each component, it's 8 and 9 and 10. Okay, and basically index I to index I plus 1, so components are included in this ith row. Okay, and so this is how we calculate, utilize this information. And the item is a column ID, and the AMAT is a matrix component. And so the size of the item and emat is NPLU. And okay, this number six element component is number 4 for the column and 1.5 for the emat. So this is number 18 and column ID is 2 and so matrix component is 2.5. Okay. So in this way, we store the column ID and the matrix component. Does it make sense? Okay, so this part is very important and so very useful for the practical programming. Actually, no classes in the world in the undergraduate and graduate class lectures teach this type of information. Okay. Okay, so if you understand these components, okay, so yeah, you can go back to this algorithm. Okay, so diag, index, item, and emat. So this is how we compute the matrix vector multiplications. Okay, so we have two loops here. So outer loop is loops for each row. Okay, and so inner loop is for each non-zero Hahn component. And so I is the ID of each row. And you can see, so this K is starting from index I and ending at index I plus 1. Okay. And so yi is equal to diagonal component multiplied by x. Okay. And yi is equal to, so summing the emat k multiplied by x item k. So item k is so column ID, and x item k is a corresponding vector component of this x. So in this way, so you can calculate the matrix vector multiply. Okay, so any questions at this point? Okay. Okay, so yeah, it's a good question, but basically we can keep the same way in the parallel computing. Yeah, because so in the case of the parallel computing of the finite element method, you apply the so-called domain decomposition. And we treat this type of operation in each domain locally. So in that case, we don't need to consider so much about the parallel computing. So yeah, I'll talk about that on probably Wednesday or Thursday. Yeah, it's a good question, but actually it depends on the application. So yeah, certain kind of applications, you have to think about that. Okay. But in the case of the finite element, it doesn't matter. Basically, we can just extend the same idea to the parallel computing. Okay. Any other questions? Yeah, because we have very few participants, so yeah, let's interact more. Okay, you can ask me any type of questions. Okay. Okay, so next part is about the more details of the program. So you can get the information how we implement these algorithms. So far, I talked about so much things. So starting from the Galerkin method and the weak formulations, and also the piecewise linear elements, and the matrix assembly, and solving matrix using the preconditioned conjugate gradient method. And finally, I talked about the matrix storage. Okay, and so in the next part, so you can understand how we utilize these method. Okay. So this is a typical finite element procedure. So it's same as so we are starting from 1D, and 1D and 3D are basically same. Okay. So starting from the reading control data, and the node of the connectivity of the elements are defined. Okay. N is a node I number, and NE is an element number. And the initialization of the arrays and the element global matrix mapping. So it's an index and item. So next part is a generation or assembly of the matrix. Okay. So basically, so they are based on the element by element operations. Okay. And we construct the element matrices and accumulate them to the global matrix. And finally, we apply the boundary conditions and we solve the problem by the linear solver. Okay, so this is the starting part of the 1D.C. And both of the 1D.C and 1D.F is a single code. They have no subroutines or internal functions. Okay, so they are just a single program because it's a very small one. Okay, so we have a lot of variables here. And so we summarize these variables in some tables. These are the name of the variables of our arrays. These are the types. I is the integers, R is the double precisions. So size means size of the arrays. So if it's blank, they are scalar. And IO is not a so strong meaning. So I is just input. O is just calculate inside the program. And I/O is so input the data, but it may be changed in the program. So NE is a number of elements. N is a number of nodes. NPLU is a non-zero components. And the iter max is a max iterations number for conjugate gradient. It's an upper limit. So it's a error flag. And RZQPDD. So these are the integers. It's a name of the vectors in conjugate gradient method. Dx is a mesh size. Logit is a residual for conjugate gradient. And the EPS is a conjugate gradient. Convergence for the convergence criteria for conjugate gradient. Sorry. So it's the -8 in this program. Area is a sectional area. QV is a heat generation. It's a Q dot. Cond is a thermal conductivity lambda. So next page is oops. Oh, there are arrays. And X is a location. Y is unknown, right-hand side vector, and this is a diagonal components. So this W is a work array for conjugate gradient method. The size is 4 by n, the two-dimensional arrays. So AMAT is the index and item are already you are familiar with. And ICEL node is a node ID for each element. And the KMAT and the EMAT are 2 by 2 arrays. So they are element matrix arrays. Okay. So first, we read the control data, and this is the control data. And we read the NE, and the DX QV area cond. Eta max is here, and EPS is here. And generally speaking, in the 1D case, number of nodes is 1 plus element number. So N is a node number, and internally, N is equal to NE plus 1 is calculated. So next part, we are allocating arrays, okay? And you can easily so allocate a phi or x or diag, so because their size is n or n plus 1. But the problem is so a mat and item. So the size is NPLU, as I mentioned in the previous page. And NPLU is not known usually at this stage. But in the 1D case, so you can calculate the NPLU before computation because it's a very structured geometry. Okay. Actually, so NPLU is equal to 2 by n minus 2. Okay. And you can see, so if you consider each node, we have usually 2 neighbors. Okay? So that means number of non-zero dynamic components for each node is 2. But in the case of these boundary nodes, number 1 and number 5 in this case, they have only 1 neighbor. Okay, so we just reduce these cases. Okay, so 2 is for the internal nodes, and this number is 1 at the boundary nodes. Okay. Therefore, total number of the non-zero dynamic components is 2 by n minus 2 plus 1 for each boundary node. And finally, it's 2 multiplied by 2n minus 2. So that's why we are allocating the size of the AMAT and item as 2n minus 2. Okay. The last one here is ICEL node. So ICEL node is storing the node of each element. So the size is NE, so number of elements, but they have 2 components. So we have 2 NE is the size of this array. Okay, so we are doing this 3-diagonal matrix. Okay. Okay, so next part is allocating the 2D arrays was a W, and it's allocating this way. So actually, in the case of the C program, we need a lot of statements allocating these 2D arrays. Okay. So next part is initializing the arrays. Okay. And phi, diag, RHS, AMAT are all initialized as 0. Okay. Yeah, as you know, it's not assured what type of the values are in the arrays or variables. So basically, most of the compilers set 0 at the beginning, but it's not specified. Okay, and sometimes it has a very funny numbers. So in order to avoid that, so we just initialize. Yeah, in this type of the scientific programming, initialization of the arrays are very important. Okay. So next part is x. So x is a coordinate of each node. And this is done by xi is equal to I dx. Okay, so dx is a mesh size. Okay. And the next part is defining ICEL node. And actually, so this is a 1D case, and the numbering is very structured. If the ID of the mesh is ICEL, node ID of this one is equal to ICEL. Okay? And this one is ICEL plus 1, according to the definition of the geometry. And ICEL node, ICEL is equal to ICEL. And ICEL node, ICEL plus 1 is equal to ICEL plus 1. So that we store the information of the node ID of each mesh. Okay, so KMAT is so related to the element matrix. And in the definition, so K is a so element matrix here, but this K mat is a little bit different. So K mat is just storing this part. Okay, so this lambda A over L is so separated here. So we are just storing K mat. You can see diagonal component are 1, and the non-zero diagonal components are -1. Okay. Any questions so far? Yeah, basically, in the case of the finite element, data is very important. Okay, and so in the case of the 3D case, we provide a mesh generator, and they generate a mesh. But in the case of the 1D program, we generate meshes internally. And most of the computations are spent for preparing the data. Real computation part is very small. Okay? And the next part is constructing the index and the items. So first one is an index. Okay? First, we put all the values of component of the index I is equal to 2. Okay, but the index 0 is 0, and the index 1 and the index n are 1 here. So at this stage, content of this array index contains the number of non-zero diagonal components in each row. Okay, you can see, so at the boundary nodes, they are 1, and the internal nodes, they are 2. And so index 0 is equal to 0. So that means, so they are storing these values now, okay? And after that, we do the accumulation. Index I plus 1 is equal to index I plus 1 plus index I. So thus, we can calculate these accumulated value. And the NPLU is equal to index n. And you can check. So this NPLU is equal to 1 minus 2. Okay. So thus we generate the index. So next part is calculating item. It's so column ID. Basically, so if you are considering the number I node, I minus 1 and I plus 1 are the corresponding column ID for non-zero diagonal components. So we are going through all nodes. So JS is the starting point of the index I. So these values. Okay? If I equals 0, so I equals 0 is this boundary nodes. So in that case, so item JS is equal to I plus 1. Okay. If I is equal to n minus 1, it's another end. Item JS is equal to I minus 1. So in these boundary cases, we have only one neighbor. Okay. But other cases, so internal nodes, so they have two neighbors. So item JS is equal to I minus 1, and the item JS plus 1 is equal to I plus 1. So that we have calculated the contents of the index and also item. Okay. Now we are ready for calculating the matrix components. So we have already defined the all arrays in integer format. But so next we are trying to do the real numbers. Okay. Okay, now it's 2:59, and it's a good time to stop and take a 10-minute break. So any questions? Okay, so now it's 3:10, and let's start the next part. So next part is a matrix assembly. Okay, and here we are constructing the element matrix, and it accumulated to the global matrix. So this is a 1D case, and it's very simple, and the whole things are included in this a single page. Okay, so basically, so we are calculating the element matrix here. We are accumulating these to the global matrix. And finally, we are calculating the right-hand side. That's it. Okay. So first, basically we are visiting all elements here. And IN1 and IN2 are two nodes. So this is based on the ICEL node. And X1 and X2 are the coordinate. And the DL is a mesh size. So basically it's a uniform mesh, but it's a difference between X2 and X1. So next part is calculating the CK, and the CK is area conductivity divided by DL. So it's corresponding to this value. Okay? And the Kmat is this part, and Emat is the element matrix is equal to the multiplying this CK to each component of the Kmat. Okay. So actually, value of the CK is constant in this case. But as I mentioned, so the important and convenient things in finite element is we can handle the different properties of each element very easily. So you can change this for each element. So that's why we keep this type of the computation. Okay, so that's it. So we have already computed the element matrix. And the next thing is accumulated these into the global matrix. So we have 4 components, okay? And the 2 of them are diagonal component. And we are just accumulating each component to the diagonal component for IN1 and IN2, where IN1 and IN2 are ID of each node. And the next one is accumulating these non-zero octadiagonal component to the global matrix, Kmat. Okay, and the corresponding address of the Kmat is K1 for this one, and the K2 for this one. Okay, so this one is a little bit complicated. Okay, and you can see. So basically, if you have a certain node, so I-1 is the index I, and I plus 1 is the index I plus 1. So this is a non-zero orthogonal components for I row. So basically, IN1 and IN2 is a relationship like this. Okay, and so this K1 is corresponding to the address for the IN2. So this means K1 is basically index IN1 plus 1. Okay. And the K2 is also index IN2. Okay, like this way. Okay. But we have some exceptions. If you have this number 0 cell, we have no mesh in this neighbor. So in this case, K1 is index IN1, okay? Not the index IN1 plus 1. So this is the only exception. Okay. So you can see how to define the K1 and K2 here. So in the case of the finite element, so especially in this type of the 1D case. So we need to be careful about this type of exceptions. So in the case of the parallel computing, it's more complicated actually. Yeah, although we are based on the same strategies, and it's a little bit different. But anyway, so this is a so definition of the K1 and the K2. And after that, we just accumulate these values into the each component of the AMAT. And finally, we calculate the right-hand side. Okay, so right-hand side is before we calculate this QN. QN is corresponding to this QAL divided by 2, 0.5 QV area and dx. Okay, and we just distributed these two QN to the both of the IN1 and IN2. Okay, thus we made the matrix. Any questions for this part? It's very simple. And even for the 3D case, we are based on the same idea. So we actually, in the 3D case, we have 8 nodes for each element, and we have a lot of computations. The basic idea is the same. Okay, so next part is a final part before solving the equations. It's a boundary condition at x equals 0. Okay. So this is a problem setting. So what we are doing here is trying to define this boundary condition. So t equals 0 at this point. Because this is a Dirichlet boundary conditions. So linear equations at this x equals 0 is t1 equals 0, or in the case of the C, t0 equals 0. So this is the equations for this part. And this part is separated from other computation part. And so matrix operation is also a little bit different. So this is a matrix, and this is the right-hand side. So what we have to do here is applying T1 equals 0 for this row. This means diagonal component is equal to 1, and the right-hand side is equal to 0. And these off-diagonal components are all 0. Okay, so that's to be done. So in this case, so we have this I equals 0. And actually, we have only one neighbors, so only one such non-zero diagonal component. It's index I. Okay, and the AMAT JS is equal to 0, and the diagonal component I is 1, and the right-hand side I is equal to 0. So that's it. But so this kind of the operation collapses some symmetric feature of the matrix. And so actually, even if you apply the non-symmetric matrix for this conjugate criterion method, it works. But the convergence is a little bit slower. And in order to avoid that, we keep the symmetric feature of the computation matrix. So in order to do that, we need to erase this corresponding column part. Okay. So by the way, so the matrix is symmetric, but we keep the all components because so we need more memory, doubled memory, but computation is more efficient. So yeah, we usually keep all the components of the matrix. Okay, so in this case, so you can go through the all non-zero diagonal components, and if the connected column is equal to 0, AMAT is equal to 0. So that's it. Then you can do this red part. Okay, column components of the boundary nodes move to right-hand side and eliminate for keeping symmetric feature of the matrix. So in this case, just erase the orthogonal component. Because in this case, the value of the boundary node is equal to 0. And in that case, you just clearing these corresponding non-zero orthogonal components. But if this right-hand side is not equal to 0, in that case, so it's a little bit complicated. So you need to find the all component. And if you find such a node, so first you have to do is moving the distribution from this boundary nodes to the right-hand side, like this way. Then clear the A map. Okay. Yeah, if it's non-zero, you need to do this. Okay. And if it's 0, right-hand side doesn't change, so you don't need to do this. Okay. And as for this end, because it's a insulated boundary where the gradient of the t is equal to 0. So in that case, we don't need to do anything. So just keep it, okay? As I mentioned in the main part. Okay. So if you have a certain value of the some heat through this surface, so you just define this value, okay? But in this case, because it's 0, you don't have to do anything. Okay, so any questions about the matrix assembly and boundary conditions? Okay, so after that, we need to solve the linear equations using the preconditioned conjugate gradient method. We apply the diagonal scaling for the preconditioning. Okay, so this is the beginning of the conjugate gradient solver. And you can see, so W is the 2D arrays. And the first index is 0 to 3. And the second index is 1 to n, or 0 to n. And here, R, Z, Q, P, D, D are defined as 0 and 1 and 2 and 3. So these are corresponding to the name of the vector, which is appearing in this pseudo algorithms. Okay? And W0I is actually a WRI here. And it's corresponding to this R residual vector. And you can see Z and Q don't appear simultaneously. So in this program, okay? Because so Z is calculated here. And actually, so this is the last point Z appears. So it's used P. And AP equal Q, and you can see no Z's here. So yeah, in that case, you can use the same address for Z and Q. That's why both of the Z and Q are equal to 1. And the P is equal to 2. And the last one is DD. So DD is corresponding to the reciprocal number of the diagonal component. So it's for the condition method like this way. Because in this type of the preconditioning, so every time you need to divide each component of R by diagonal component. But generally, dividing is more expensive than other procedures. Adding, subtracting, and so multiplying. And when I was a student, so more than almost 40 years ago, in the summer internship, so I worked for Hitachi, and so I evaluated the performance of the Fortran compiler. And I realized that so dividing is much more expensive. So more than 10 times slower. Okay. Actually, so each operation is fast, but so dividing, if you iterate 100 and 1,000 times, so it's not negligible. And so rather than dividing every time, it's better to multiplying the reciprocal number. So that's why I so suggest this method. So actually, in the modern so architecture, it's not so slow, okay? But rather a little bit slower, and it's better to apply the so this multiplying. Okay, so this is a so beginning part, and we are calculating the initial residual. Okay. Actually, I don't remember where, but x equals 0. Okay. But so you can see, so we are calculating the so initial residual here. Here, each component r is ax0, and at this part, r is equal to right-hand side minus r. Okay, calculate here. And also we are calculating binom2. So binom2 is the sum of the square of the each component of the right-hand side. Okay, so it's corresponding to the so square of the length of the this vector. Okay, so this value will be used for the convergence criteria of the conjugate gradient solvers. And please remember this number. Okay. So next part is so main part, and the iteration is from 1 to eta max. Okay. So first one is pre-conditioning. So this part is very easy. Each component of z is equal to so each component of dd multiplied by so r. Okay. So instead of dividing by the diagonal component, we are so multiplying the reciprocal number. And the next part is rho equal rz, and it's also simple. So initial value of rho is equal to 0, and we are just visiting all components of the so each row, and ri and zi is calculated here, and it's accumulated to rho. So this is the typical operations for dot product. So next part is the updating p. So here it's the first iterations. P is equal to z. So it's according to the definition of the p. So otherwise, beta is equal to rho divided by previous rho, rho 1. And p is equal to z plus beta. Okay. So this one is a previous p, and this one is a so current p, new p. Okay. So yeah, we are just following this. And the next part is the q equal ap, and we are calculating that according to the CRS format, which I mentioned before. First, so yeah, outer row loop is for each row, and first we calculate the contribution from each diagonal component. After that, we calculate the contributions from non-zero orthogonal component, from index I to index I plus 1. Okay. Then we are calculating each component of Q. Okay, so next part is calculating alpha. So alpha is rho divided by PQ. And PQ is not explicitly defined in the program, in the so algorithm. And we assume the name of this value as C1. Okay, so C1 is equal to the so dot product of the PQ. And alpha is equal to rho divided by C1. Okay. So next part is updating x and r, and x is defined as a phi in this program, and each component of x and r are calculated by so these formulations. Okay. So this is a typical DAXP operations. Okay, final part is checking the convergence. Okay. So we check this value, it's a norm of the residual vector. Okay, if this is small enough, it's considered as converged, and otherwise we need to repeat the iterations. Okay, so this checking convergence is very important part. Okay, so in order to define this convergence, first we calculate the d norm 2. So d norm 2 is the sum of the square of the each component of R. Okay, but finally, so we define the residual by square root d norm 2 divided by b norm 2. Okay, so actually, if this rigid is smaller than EPS, we can go out. So otherwise, we repeat the loops as row 1 is equal to row. It's a previous row. And what is this rigid? Okay. So rigid is d norm 2 divided by b norm 2. Okay. And we take the square root. Okay. So that means length of the vector of the R and B. Okay. And R is equal to B minus AX. And if it's smaller than this EPS, it's considered. So otherwise, we repeat the iterations. So R and B, more precisely, it's called norm or L2 norm or Euclidean norms. And you need to write in this way. Okay, so you just check the double bars, and the 2 is L2 or 2. Okay, it means we sum the square of each component and take the square root. Okay. So anyway, it's corresponding to the length of the vector. Okay, so this means we don't evaluate the convergence just by this R vector, but it's divided by B vector. And this kind of computation is called normalizations. And it's normalized by the right-hand side vector. Okay. And so this rigid EPS is corresponding to this 10 to the minus 8. Okay. So why do we need this normalization? Okay. If we consider the two kinds of the equations, AX equal B and alpha AX equal alpha B. If the alpha is a real number, you can easily recognize X are same or these two equations. Okay, but if we apply the same X, residual vector for this one is a B minus AX. But residual vector for this one is alpha B minus alpha AX. So this is corresponding to alpha R. Okay, alpha is equal to 1, it's okay. But so alpha is not equal to 1. So it takes a different convergence history. So basically, in order to avoid that, we normalize by this B. Okay, so that's why we need to do this. Okay, does it make sense? So basically, this conjugate gradient part is same for the 3D case. Okay, and we are mainly work on the 3D case, but in the 3D case it's same. Okay, so this is the finite element procedures. And so I just show you some remedies for higher accuracy. Okay, so actually, as you remember, in our case, even if we apply just 4 elements, they provide the exactly same answer for the analytical solutions, because it's a very simple case. But for example, if the sectional area is changed as this as a function of the location, it's a little bit more difficult. Okay. For example, this is a n equal 8 elements, and you have a mesh size at 12.5 and 8 iterations, and so residual is this number. Okay, and this is a computation, and this is a analytical solution. Okay, so you can see at the end point, yeah, it's obviously different. Okay, not as our case. Okay, and if you increase the number of elements from 8 to 20, so it's more than doubled. So in that case, you can see, so the results are very close, but it's still different. Okay. But anyway, so finer meshes sometimes provide so better solutions. Okay. And so yeah, in our case, it doesn't change, but so sometimes finer mesh provides a better case, better result. So another approach is a higher order shape functions or higher order interpolation functions. Okay, it's called a higher order element because now we are using a linear element, and it's a first order element. So basically, it's a lower orders. Okay. And another approach is a formulation which assures the continuity of nth order derivatives, and it's a Cn continuity. Okay. Linear elements is a so piecewise linear and C0 continuity, and the only dependent variables are continuous at element boundary. Okay, so it's a C0 continuity. So actually, so C1 or C2 continuity is very, very difficult and very expensive, and we usually don't use this. Okay, basically, we are using the C0 continuity. And the next one is also another type of the more complicated heat transfer. It's a cylindrical shape, and we have some convection so around the cylindrical surface. Okay, so by these boundary conditions. Okay. It's a little bit complicated, but it also has so analytical solution like this. So this is the exact solutions, and it's so temperature is going down and down in this case. So this one is a result for the so linear case using 4 elements. Okay, and this one is a so we doubled the so number of elements. Okay, and you can see if you compare the error at so this end, it's a 0.4%, and this one is a 0.1%. So this one is keeping the same number of nodes, applying the quadratic interpolation, so second order interpolation. So in this case, we don't use the number of nodes, but you can see, so we have a very significant improvement from the viewpoint of the error. It's a 0.02%. It's very small. Okay. Okay, so this is an implementation of the 1D quadratic element. Okay, so in that case, we have 3 points, and usually, so this so midpoint is so mid of the half of these two, and we have so this type of the second order functions of x or the shape function. And then we can define the A1, alpha 1, alpha 2, alpha 3 in this way. And so this is so these 3 are shape functions, Ni, Nj, and Nk. So generally, so xi is equal to 0, and xk is equal to L, and xj is equal to half of L. Okay, like this way. And so in the case of the element matrix is in this case 3 by 3 because we have 3 nodes for each element. And we need to calculate these. And so we can calculate this analytically. And this is a resulting element matrix. And as for the right-hand side, so in this case, it's distributed in this way. And so 1 by 4 by 1, okay? The midpoint has more contributions. Yeah, in the case of the linear element, like this way. Okay. Okay. And then this is a formulation for the 1D linear element. And in the case of the quadratic element, we have 3 nodes for each element. And in this case, we have only 2 elements. Okay, so number of elements are half. Okay. But you can see we have a much more accurate solution. Okay, like this way. So actually, it depends on the problems. But generally speaking, if the problem is smooth, so rather than applying more nodes or finer meshes, it's better to apply the higher order functions. Okay. So in this class, we are just focusing on the linear elements. Okay, so last part is just appendix. And so we just keep this linear element. And yeah, in the case of the real world problems, we need to care about these things. Yeah, even for this type of the very simple problems, so the mesh number affects accuracy very much. Okay. So any questions so far? Okay, so we still have some times, and so as I mentioned, the last slot from 4:10 to 5 o'clock is some optional exercise because this is the first day, and you should be very tired. Okay, so and yeah, you can leave after 4 o'clock, and also you can stay here. I will stay here, and if you have any questions, you can ask me. But we still have 15 minutes until 4 o'clock, and I just make a brief introduction of the 3D part. Okay, if you have no more questions. So let's go to this 3D part. In 3D, we are also solving the heat conduction, steady state heat conduction. And in that case, yeah, it's a 3D. And so basically, T equals 0 at this top surface. And we apply the insulated boundary conditions for other part. But if you apply the uniform heat generation, it's a 1D problem. And in order to apply the 3D problem, this Q dot is a function of the XYZ location of the each cell center, okay, mesh center. Yeah, actually, it's a linear problem, but it's a real 3D problem. And lambda is equal to constant, and the hexahedral meshes, and mesh size is 1 in each direction. It's a unit cube. And the number of meshes in each directions are defined as nx, ny, and nz. Okay. And so actually, so this is so xc and yc is a coordinate of the mesh center. Okay. So in this case, we just consider the x and y. Okay. And we just sum these two. And this means, so if you are away from the origin, so you have more heat generation. Okay. Okay, so this is a result for the 3D problem. Okay, we have a movie here. Oops. Asuka. Just a moment. I didn't install the software, but okay, I made it. Okay, so this is a result, and this is a origin. Okay, and the red is a higher temperature, and so you can see origin has a yellow, so it has a lower temperature. And the top surface is 0, and you can see if you go down, you have a higher temperature. Yeah, I think it's better to show you the paraview. Just a moment. Oops. Okay, and okay, so you can see this. Yeah, color is not so exciting, and you can see top surface is 0, and you can see if you go down, you have red colors. And this is the origin, okay? And you can see the color is a little bit light. And if you are away from the origin, so the color is darker and very red. So this is because heat generation value is larger if you are away from this origin. So that's why you have this type of the distribution. Okay. Okay. And this is the procedures for the finite element method. And we are starting from the governing equations, Galerkin method by weak form, and constructing the element matrix by element integrations, and constructing global matrix, and applying the boundary conditions, and solve the linear equations. Basically, it's same as a 1D, but in the 3D case, each part is a little bit more complicated, and we need more lines of programs. Okay. Yeah, this is a same thing. And this is a overview of the 3D part. So actually, formulation part is the same as the 1D, and but so this part is the same. But so I just introduced the very beginning part of the 3D element. Okay. Actually, so this Galerkin method part is same. Okay, before going directly to the 3D, we should think about the 2D. Okay, and actually, so if you read the textbooks for the 2D finite element method, generally they are mentioning about the triangle meshes. Okay, and the triangles is very convenient, and it can handle arbitrarily shaped object. So it can model the very complicated geometry. And for example, this is a mesh for the tsunami simulation, which I did long time ago. It's a Kyushu island. So this one is a Shikoku island. This one is a Kii Peninsula. And the triangles can so resolve the very complicated coastline in this way. So it's a, this one is a coarse mesh, and this one is a fine mesh. But generally speaking, linear triangular elements provide a very low accuracy. So therefore, they are not used in the practical applications. Okay. And the higher order triangles are so widely used, but higher order elements are a little bit complicated. And it's not so feasible for this type of lectures, where we are focusing on the parallel computing. And so we are using the quadrilaterals in the 2D and hexahedrons in the 3D problems. But anyway, so triangular is one of the choices. Okay. Okay. If you apply that, so quadrilaterals, and the formulation of the quadrilateral element is possible if the same shape function in 1D elements are applying along x and y axis. So it's generally more accurate than triangles. But each edge must be parallel with x and y axis. So it's similar to finite difference method. Okay. For example, this type of so arbitrary quadrilaterals cannot be considered in this type of the formulation. So in order to avoid that, or in order to tackle such kind of problems, we introduce some special coordinate system where we are transforming this type of the arbitrary shape in this type of the very structured meshes. So in this case, from the XY coordinate system to Guzai eta coordinate system. And where you can see so each node is mapped to this one. And so all of the coordinate of the so 4 nodes are plus minus was a plus minus 1 was xi and eta. So this type of coordinate system is called natural coordinate system or local coordinate system or element coordinate system. We have many names, but I like this natural coordinate system. Okay. So anyway, so xy is mapped to plus minus 1 xi and eta. Okay. So components of the global coordinate system of each node for certain kinds of elements are defined by shape functions n on natural coordinate system, where shape functions n are also used for the interpolation of the dependent variables. So this means, so in this case, we are so independent variables, so dependent variables are temperature, and we also use so this type of the shape functions for the x and y simultaneously. And this is a so idea. Okay, so we have a actual coordinate value x and y from 1 to 4, like this way. Okay, so these are some arbitrary value. And the temperature at each node is a T1, T2, T3, T4. And the shape function itself is defined as so this local coordinate system or natural coordinate system. And T is equal to the so this linear combination of Ni from I is equal to 1 to 4. And the X and Y are also calculated by this way. So it's a little bit complicated. Okay. So here we are applying the isoparametric elements. So isoparametric means the same parameter. And in this case, we are using so Ni for X and Y and Ni for the T are same. So we are applying the same shape function. if you apply the higher order shape functions, so they can handle the curved lines or curved surfaces very easily. So that's why we call this natural coordinate system. So even if we have this type of the curved element, so you can define that on this type of the structured mesh. And the superparametric is a higher order Ni for x and y. And the subparametric is a lower order Ni for the x and y. So we are applying the isoparametric. In that case, same order Ny for the xi. Okay. Yeah, sometimes we apply these in certain kinds of the applications, but generally we apply the isoparametric elements. Okay, so let's think about the shape function of this 2D natural coordinate system, xi and eta. Okay, so if it's linear, t is equal to alpha 1, alpha 2 xi, alpha 3 eta, and alpha 4 xi eta. So we have 4 components. Okay, and because we have 4 nodes, and so according to this temperature, you can define the alpha, alpha 2, alpha 3, alpha 4 in this way. Okay? And if you put these values into the original equations, and if you reorganize these equations according to T1, T2, T3, T4, so finally, you can get this type of the equations, or the definition of the T. So you can see, so it's multiplying 1 plus minus xi and eta multiplied by 1 over 4. Okay, and this one is N1, N2, N3, and N4. And you can see, so this is a shape functions for the 2D natural coordinate system. Okay, 1 plus minus eta and xi. Okay, so t is equal to the linear combination of the niti from I is equal to 1 to 4, and each of the shape function is defined by this way. So this kind of formulation is called out of battery or bilinear interpolation, because it's linear in each directions, and it's bilinear interpolations. So in the previous part, in the 1D part, I described the feature of the shape functions. Okay, and let's calculate the Ni at each node. Okay, because xi and eta are plus minus 1, and you can calculate the value of the N1 and N1, N2, N3, N4 for each node. For example, N1 is equal to 1 at this point, because this coordinate is -1, -1, and 1 minus -1, and 1 minus -1 is that, so 2 by 2, and divided 4 by 4 is equal to 1. But if other point, at least one of them could be 0. So that means as a number 2, 3, and 4 point, N1 is equal to 0. Okay. Anyway, so you can confirm that by yourself. Okay. Okay, so this is a very introduction for the 3D part. And first, we define the shape functions of the 3D natural coordinate system. And we extend this idea to the 3D. Okay? But basically, please review this part carefully. Okay, it's 4 o'clock, and we stop here today. And any questions or comments so far? Okay, so thank you very much for joining, and so see you tomorrow, 9:10. Thank you very much.